Okay, so today we're going to do the 470 final review. So we're going to be going over a lot of the major topics that you should be familiar with for the final next week. So an important thing to know is just like basic starting out is you have an input, right? So we're in the discrete domain, so that's why we have n here instead of t. And so this input is coming in to a summing block. And so, oh, sorry, right here, this is a minus sign. And so we have this input coming into the summing block, and then we have a controller. And so within our controller here, this is operating in the discrete domain as well. And then what comes after a controller, just for a general overview, is this is the digital to analog converter because we have to convert over to the analog domain in order to operate with our plant, because our plant is normally in the continuous domain here. And so we have to convert that signal over to an analog one from the discrete time. Then after it goes through the plant, it's going to head back and we're going to have a feedback path. Along that feedback path, there is probably like a sensor. And that sensor is going to be collecting information. And then after, we have to convert it back to a digital signal. So we have an analog to digital block here, and then it feeds back. So what we're going to see here within our design is that there's part of this that is digital and there's part that's continuous. And so what's done by the computer normally is normally we see the part right here is done by our computer. So this is all happening usually in the discrete domain. The input signal is generated by the computer. The controller's computerized digitally, and then we have to convert it to analog so it can work with our real-world system here. And so then our real-world system from our controller is going to generate an output. So this is in the continuous domain here, the output y of t. And so right here, what happens is you'll have still your discrete signal, but after digital analog converter, it becomes your continuous signal. And so that's your real-world output. And then the plant and the sensor are in the continuous domain. They're physically happening in the world. And so what we're going to do is we're working the discrete environment with the continuous environment. So that's what this is trying to say here. And so some important things just to know is that when we have to do the starred transform, to get familiar with what that is, because that's an operation that we use a lot, the starred transform helps us convert, basically. It's like an ideal sampler, because a lot of times we have to sample signal coming in. So sometimes this input signal might be continuous here, and then we have to sample it before. So sometimes this analog to digital might be over here. So you might see this block come after here, because this might be a real-world input here, and then we have the real-world input here, and then we convert it digitally right before the controller. So sometimes you might see this block over here, and this might be a real-world input. So for those types of variations where you might see those types of problems, you need to know the star transform, which is basically like an analog to digital converter. That's what it's trying to act as. So it says f star of s is equal to, and then we have the summation here from 0 to infinity. And then it's going to be f of k of t e to the negative kts. And so what you're going to see here is basically what you're going to notice is you're going from 0 to infinity. So how many points you have along here. So you're going to have infinite points of your waveform. And so what we're also going to see is the star transform can be written in the following format. So it's not only that type, but it's also the summation. So if this one doesn't work for you, you can use this alternative. So make sure you have both. If you're at the poles of f lambda, and so you're probably wondering what is f lambda? We'll do an example with it. It's the residues of f lambda, and then it's going to be 1 over 1 minus e to negative t, s minus lambda. Okay. And so here, what we're going to have is these are the two ways you can calculate the star transform. So this is sort of acting as your analog to digital converter. you're taking your signal basically and converting it into the digital domain. And so what we're going to see from here is for our example, say if we have a continuous signal. So our continuous signal is given by f of t is equal to 1 minus e to negative t u of t, okay? So let's apply both definitions and see if we can get the same result. So let's say we want to convert this to our digital signal, after the analog to digital conversion. So what we're going to do here is for f star of s, using the first definition, we're going to see that runs from 0 to infinity. And then it's going to be f. And then notice, instead of t here, you're going to let t equal kt. So letting t equal k capital T, inside what we're going to get is it's going to be, so replace everywhere t with kt. I'm going to get 1 minus e to the negative kt, and then u of kt, okay? And then e to negative kts. So that's what I get here. Notice that this term right here starts at 0, right? The unit step starts at 0, and our summation starts at 0. So we can get rid of this term right here. Now, looking at our summation here, k equals 0 to infinity, and we have our 1 minus e to negative kt, and then e to negative kts. What you're going to do is basically we can multiply this out. And what we're going to see here, when you multiply this, you're going to get an e to negative kts, and then it's going to be minus e to negative kt, then this is going to be s plus 1, okay? So that's what we have when we just distribute. And so what you're probably going to notice is that the only thing that's changing within both of these is k, because that's what we're taking the summation over. That's the only variable we have here. T is constant, that's just your sampling time, so you don't have to worry about that. And then your S is basically, just the domain you're working in, but your K is going to be changing. So you can sort of write it like this, because if your K is the only thing that's changing, couldn't you agree with me that this looks like the x of k, where this is constant, and then to the power of k, because the k is going to be changing. So remember the summation of if you have your 1 plus x squared plus dot, because this is x to the 0, x to the 1, x to the second, because we would start off here x to the 0, because if you're e to negative ets, if you let x equal e to negative ts, you can rewrite that summation up here as x to the k, and then minus, and then what we're going to have here is going to be, and then if we take this one out, it'd be minus x, and then this one would be e to negative ts, e to the negative ts, and then e to negative k. Okay, if we distribute that, it's going to be particularly our s plus 1. Okay, so that would be, let me see, x to the k, that'd be x to the e, let this one. Oh, what you can do, just real simple, because this stuff is just constant here, if you just let this be, let this right here be y, and so then you can make it minus y and then to the k. And so here, if you let y equal e to negative t, and then s plus 1, because that is constant, the only thing that's changing is k in our summation. And so what we're going to have here is minus y to the k. And so what we're going to notice is we start from 0 and we go to infinity, which this summation, it's x to 0, x to 1, x to 2, and goes infinity. Remember, that summation was equal to 1 over 1 minus x. And so what we're going to have here is then we can substitute in that summation here when we have x of k, you can write it in terms of this summation, x to the power 0 plus x to the power 1 plus x power 2. And so that's our geometric series. So here what you're going to get as a result is you're going to get your f star of s is going to equal 1 over 1 minus x. And then you're going to have here minus 1 over 1 minus y. Now, substituting back in what your x represented and your y represented here, you're going to get f star of s is going to equal 1 over 1 minus, and what's your x? E to negative ts minus 1 over 1 minus, what's your y? It's going to be e to negative ts plus 1. And so then that would be your solution for this problem using the geometric series way. And so that's one method you can use to solve this problem. And so you just had to remember your geometric series here. This was basically when you sum up your k's, when you do the summing of your k, x to 0 plus x1 plus x2, etc., is equal to 1 over 1 minus x. And so that's what we had here. But the alternative method, remember, f of t was equal to 1 minus e to negative t u of t. And remember how we said there's two definitions for the star transform that we often use. Well, the second one, remember, relied on the residue method here. So we're going to see how this one works, and I think this one's the better one to use in my opinion, so I would use that one. It was f star of s is going to be equal to, and what we have here is it's going to be the summation at the poles of f lambda, and it's going to be the residues of f lambda, and then 1 over 1 minus e to negative t s minus lambda. Okay, so here what we have to do basically is we're going to solve our system. So notice that we have f capital. So right here we're with f lowercase. We're with lowercase f. So we have to convert this over to capital F. So taking the Laplace transform of this, let's just look at that first. So finding the Laplace transform, if we multiply that out, we'd have a ut minus e to negative t ut. So looking just at our f of t real quick right before, so it makes sense, it's equal to u of t, if you just multiply that out, minus e to negative t ut. Then if you apply the Laplace transform on that, f of s, remember, Laplace transform of ut is 1 over s minus. And then here, the Laplace transform of e to negative t ut. So we have a minus sign in front because minus sign here. This is going to be 1 over, and then you have s plus, and then what's the coefficient right in front of this t? Notice that it's a 1 right here because the negative sign makes this a positive down here. So it's 1 over s minus 1 over s plus 1. That's just from your Laplace transform table, so include that if not on your paper. So now we have f of s right here. And so what if I want it in terms of f lambda? Okay, what I'm going to do is I'm just going to replace the s with the lambda. And so 1 over lambda plus 1. Okay, now that we have that, we get our f star of s is equal to, and then what we're going to have here are poles at 0 and at -1, right? When you make that denominator equal to 0, you get lambdas equal to 0 and lambdas equal to -1. So that's where my poles occur. Now, what we're going to have is our residues of f lambda here. So we're going to have to do residues of, and what's our f lambda? It's 1 over, making a common denominator for this, so you guys know you're going to have 1 over, and then lambda plus 1. If you just make this all one common denominator, so lambda over lambda plus 1, and then in the numerator here, you'd multiply it by lambda plus 1, and then here by lambda, so lambda plus 1 minus lambda would just be 1. And so this is your f lambda, just written with one common term in your denominator, and then you have to multiply it by 1 over 1 minus e to negative t s minus lambda. Okay, so now that we have that, what we're going to do is now we have to solve this. So using our residue method, what we're going to have is we're going to have our f star of s is equal to your first pole's at 0. So that's your first residue, lambda, and then it's going to be multiplied by 1 over lambda, lambda plus 1, and then it's going to be times 1 over, and then 1 minus e to negative t, and then s minus lambda. And that's evaluated at, well, right now we're looking at the residue at 0, right? When lambda's equal to 0, that's when you get your pole. And so that's when lambda's equals 0. Okay, and what's your next residue? Because remember, it's the summation of your residues. We accounted for the 1 at 0. We need to account for the 1 at negative 1. So multiply by the lambda plus 1. And then it's going to be 1 over lambda times lambda plus 1. And then times 1 over 1 minus e to negative t. And then s minus lambda. Evaluated at lambda is equal to negative 1. Okay, now that we got that, what we have to do here is we're going to have to solve. So looking at what cancels, you're going to notice this lambda and this lambda here cancels. This one cancels. And now plugging in what we have here, you're going to get, for this term, when you plug in 0 for lambda, you get 1 over 1 times 1 over 1 minus e to negative t s, and then lambda 0. And then what about this term here? Well, we're going to get, when you plug in negative 1, it'd be 1 over negative 1, so that'd be a minus sign here. So we're actually going to have a minus sign. And then it's going to be 1 over 1 minus, and then e to negative t. And then it's going to be s, and then plug in negative 1 for lambda, so you get s plus 1. Okay, now that we got that here, notice that this answer is exactly the same as this one down here. So you can use either method. I think this method, though, is easier in terms of it applies a lot more places. So I think you should use this technique. So that's our f star of s. That's what the star transform does. It basically just converts it from our continuous domain. Notice that now we have our sampling time here, capital T. So it converts it from the continuous domain to our discrete domain. So it's an analog to digital converter, basically what's happening. Okay, now that we talked about that, the star transform, we're going to look into a little bit with our next one. So let's see. This one I think is a good example to at least have a little exposure to, because it has two poles. So I think it's important to know how the residue method works for this one. So our next example is going to have f of t is equal to t u of t. Now remember, when you have to find the star transform, you have to find the Laplace transform of this one. So this would be f of s is equal to, and then you have this would be 1 over s squared. Now, remember, in the star transform, you need to just have it in terms of lambda, so it's 1 over lambda squared. And then what we have, remember, definition of the star transform, it's equal to, and then it's the summation. Where are the poles? They're at 0, right? When lambda is equal to 0. And the residues of, and then what's our f lambda? It's 1 over lambda squared, and then multiplied by 1 over 1 minus e to negative t, and then s minus lambda. And then what we're going to see here is we basically now just need to solve it. Notice that we have two poles at the origin here. And so what's interesting about the residue method is you're going to have to take the derivative with respect to where your pole is. So you take the derivative, but you still multiply by your poles, so the lambda squared, your actual residue, and then your f lambda is 1 over lambda squared, and then you have your 1 over 1 minus e to negative t, and then s minus lambda. And so here, remember, you evaluate it. Where's your pole occurring? At lambda equal to 0. And so here we're going to notice that the lambda squared cancels with the lambda squared. So we're left with, we have to take the derivative of this term here. And so when we have to take the derivative of this term, what we're going to get actually as our result is, you have to remember, for some people, I think it's easier if you write it in terms of this way, minus t, and then s minus lambda, and then to the negative 1 here. So what you're going to notice basically happen is when you take the derivative of this and then you finally evaluate it at 0, you can see that from your calculus that you take the exponent, remember you subtract 1 from the exponent, so you would get s minus lambda, and then to the -2, so remember you have to drop the power, and then what comes in front basically here is what's attached to the variable you're taking the derivative with respect to. And so what we're going to see here is what's going to come down in front is your t e to -t and then s minus lambda. Okay, so now what you're going to get as a result is then you finally have to evaluate lambda equals 0. So that's when you have to take the derivative. Remember, when you take the derivative, you drop the power of the exponent by 1, and then everything inside that it's attached to, you have to drop then in front. So remember, we're going to have a negative sign drop in front, so that's why we have a positive here. And then the t comes in front because that's attached to the lambda, actually. And then what we have then that is attached to it is the e to -t and then s minus lambda. And so that's just from your derivatives from calculus class, just giving you a little re-explanation there. And so you're going to get t e to the -t and then s minus lambda, and then it's going to be 1 over 1 minus e to -t, s minus lambda, and then squared. Okay, and so plugging that in for lambda equal to 0, what you're going to get here is you're going to get t e to -t s all over, and then 1 minus e to the -t s. Okay, and then this is squared. Remember that. So now that we got that, that's our stored transform. So the important thing to notice here is that don't make the confusion, because we had 2 repeated poles at the origin. And a lot of times people think of, if I were trying to go backwards, remember how like when you tried to do from f of s to f of t here, this is a side note. When you try going backwards, you're gonna have to take the inverse Laplace transform. So you'd write that as a over s plus b over s squared, and you would solve for a and b. Well, here, when you do the star transform, you take the derivative to find one of yours, which we're used to, but you don't have to account for the other one. You know how you have to like an s and an s squared, split it up? Here you only do it for the lambda squared, and then you just take the derivative with respect to that and plug it in at 0. You don't have to do this like twice or anything. So just be familiar when you have repeated poles and you're trying to find the star transform, you only have to do it once, but you just have to take the derivative with respect to that term. Okay, now that we saw that, what we're going to notice specifically is there's a little bit important of a nuance we have when it comes to working in the f star of s domain. So just to be familiar with the f star of s, know that f star of s is periodic in the s plane. And what's its period? So in the s plane. So the period is going to be t is equal to 2 pi all over omega s. And so what we're going to notice here, the poles are going to be periodic along the j omega axis. So say right here, if we have like our s plane, for instance. And so if we have our s plane here and we have our j omega s all over 2, what we're going to notice, and then say if we have our negative j omega s all over 2, this is referred to right here as the primary strip. It's the primary strip because everything's just a repeat of your primary strip here. So that's what you need to basically know, is that everything gets repeated. And so then if you're solving for omega s here, you would get omega s is equal to 2 pi all over t, just so you know. So what we're going to see here is our primary strip occurs from negative j omega s over 2 to j omega s over 2. And so if you have poles, let's say, for instance, in your primary strip, the poles are right here and right here. Okay, so what's going to happen is basically if you start repeating these poles, because remember, it's periodic in the S-plane, the repeat of these poles then would occur in your next one up here. It would be just a repeat of the ones you have there, and right below, it would repeat them as well. In these ones, this would go up to J to the 3 omega s all over 2. And then down here, it would be negative j and then 3 omega s all over 2. And so these are referred to as the complementary strips because they're a repeat of the primary strip. So just note that the poles are periodic. And so if you know the poles, they just repeat basically in the F star of S plane. And so what you're going to see is if in your f of s plane, if he asks you, if f of s has a pole s is equal to s1, then f star of s, remember, it's the exact same poles in the, but the only difference is that it's repeated every, you're going to see here 2 omega s over 2, so every omega s, it gets repeated. So s is equal to s1 plus j m omega s. And so it's going to be repeated every omega s. So it's going to be for m equal to 0, plus minus 1, plus minus 2, etc. And so it's going to be the same exact location for the poles, except it's repeated every omega s. So just be familiar with that. Is if you know the poles in the f of s plane, then you know the poles in the f star of s plane, but they're just repeated every omega s. And remember, omega s here, it's going to be your 2 pi all over capital T. And so that's what we basically have here. So if you know the poles here in your f of s plane, your f star of s plane, they're just repeated every omega s. Okay, now that we saw that, basically, what we're going to do here is we need to know a little bit about how these systems work, particularly with zero order holds. Because what we focused on right now is we sort of saw the system where if we have a real world input, R of t, then it goes through a summation block. And then we have right here, it's a sampler. So we're sampling our signal. So every t sample of time. And then it goes through our digital controller. A lot of times this is represented by D as Z. And then it goes through and it has to convert it back to the continuous domain. And so we oftentimes use a zero order hold here. So it holds the signal to make it continuous at the output so that it can go through our plant function. And so our plant often here is GP of S, and then it can produce our output Y of T. And then our continuous system, this is often represented by H of S here, then gets fed back here. So we looked at the analog to digital conversion, which, for instance, if this is your E of S here, this would be your E star of S. So remember how I said the star transform is the analog to digital? Right here, sorry, if I'm writing in the S domain, this should be R of S, and this should be like Y of S for your output. And so what we're going to look at in particular is the zero order hold, because right now we have to go from the Z domain back to our S domain. And oftentimes he likes to refer to this part here. The zero order hold in your plant transfer function is referred to as your G of S. And so that's what we're going to look at right now in particular. So this is normally how we see our systems constructed. Even though in the beginning we saw this, you can do the analog to digital conversion here if you get a digital input. So to make this digital with digital and then feed it into your controller and then convert it continuous. Or we oftentimes see this type where the input is continuous. So from the real world, and we have to convert then it to digital here in order to work with our digital controller. And so what we're going to see in particular is how is our zero order hold defined? And so we went through basically like a lot of math just to understand the derivation of how this hold actually works for us. But the most important thing that you're going to see from this, zero hold is basically the definition of how it works. So let me just define that one for you. For instance, if we have our zero order hold, a lot of times is just going to be 1 minus e to negative st all over s. That is your zero order hold. Sorry, I wrote that pretty bad. So it's 1 minus e to negative st all over s. There you go. That's a better definition, but that is what is happening within your zero order hold here. And so what we were able to define for our zero order hold is if you want to find the g of s here. So your g of s is a combination of your zero order hold with your GP of s. And so our G of s is often defined as 1 minus e to negative st all over s, because that's your zero order hold multiplied by your GP of s. And so what we do with this is we take the z transform, and when we try finding the z transform, what we get as a result, so when we find our G of z, it's equal to 1 minus z to negative 1, and then the z transform of g of s all over s. Oh, sorry, GP of s all over s. Okay. So just know that when you have to find going from one form to the other, if you have a zero order hold here, and then you have to find with your Plant transfer function to find the g of z, this is when you try taking the z transform here, you're going to get the following result: 1 minus z negative 1, and then the z transform of your Plant transfer function all over s here. Because what we did is we substituted in for z from our definition. Remember, z is equal to, here it's z is equal to e to the st. That is a very important definition that we're going to see pop up to convert from our s domain over to our z domain in order to keep that straight. And so that's what we're used to seeing in order to solve a lot of our systems when you have to combine the two in order to find the z transform or g of z. This is how you would write it with a zero order hold applied. And so what we're going to do basically is looking at our systems. Let's look at a quick example real quick before we dive into this. So we're familiar with a little bit of the background terminology. So for an example, say that f of t is equal to ut. Okay. And what if we want to have to find our f star of s? Okay, so our f star of s, if we remember just our basic definition here, what we're going to see here is that our f star of s, we would use the residue method, right? So if I were to find the f of s here, it's equal to 1 over s, then finding the f lambda, just plugging in lambda, I get 1 over lambda, right? And so my f star of s would be the summation, basically the residues. The residue occurs at lambda equal to 0. And then the residues of f lambda, so multiplying by the residues, and then f lambda, and then 1 over 1 minus e to negative t s minus lambda. Okay? And so what we're going to have here is for our f star of s, it's going to be lambda, and then our f lambda is going to be 1 over lambda, then 1 over 1 minus e to negative t s minus lambda. And what we're going to notice here is that our lambdas will cancel. So lambda will cancel with lambda. And then plugging in our lambda is equal to 0 here, we're going to see that we're going to get 1 over 1 minus e to the negative ts, correct? But what did we say up here in our definition? Let's say we want to find the f of z. Well, what is our z defined as? Z is defined as e to the st. So you have to substitute in here e to the st. That's everything right here. And so it's going to be 1 over 1 minus z to the negative 1. because the negative wasn't included in the definition of z. It's just e to the st. So that negative sign's still there, so that's why you have -1. Now multiplying by z in the numerator and denominator, I'm going to get z over z minus 1. And so that is my solution for f of z. So that was just using our basic definition here. So you see, when we find the star transform, we're able to easily find it in terms of f of z. And so what you have to do to convert f of t, you find the star transform, then you can convert that to your z transform. And so we like this format because right here, it's not a rational function, but this is a rational function because this has an exponential term. That's not rational. It has to be a polynomial of s. And so here, what we see is we get a polynomial z in the numerator and denominator. So this is a rational function, which we like. That's why we like working in the z transform, because we get a rational function of something that's not normally. Okay, so now that we saw that, there's one major thing. There's an entire z transform table. So for this one, make sure you have this on your sheet, because that's really important that you have all the z transforms on there. So just make note, make sure that you include z transform table. That is very important because he will not provide that. So make sure you include that on there, just so you have it for handy reference. Okay, now that we talked about all that, where we saw how all those definitions worked, I think it's important that we look at specifically one of our examples. Let's see, I think this one would be, let me check, what is the pupils? Okay, let's get started with our next one real quick, and then we'll come back. So we're going to look at open and closed loop systems. So we talked about, our z transform, how it works, and now we have to look specifically at how those open and closed systems work within our transfer functions. Because a lot of times we have two types, our open and our closed. And so we have to evaluate how those work in the z domain. And so what we saw specifically is that we were used to writing our f star of s in the following format. So we had our f star of s is equal to. And then when we define this, remember we had our summation from k equals 0 to infinity, and then it was f of kt. And then if you guys remember, it was e to the negative kts. But when we're talking about our z transform, remember we just substitute in our e to negative ts with z. So this would be z to the minus k. So that's how you get your f of z. And so what we're going to notice here is that this is just an alternative representation. And so what we're going to do within ours particularly is we have to look at some properties of the star transform before we jump into this. And so what the star transform is defined as is, let's look at some properties of how this one operates. Properties of star transform, because this is going to become actually important. So if we have particularly our C of S is equal to, and then, so let me write it out here. If we have like let's say C of S is equal to, and then we have G of S times R star of S. Okay, and if we take the star transform on each side, so right here, if I was going to take the star transform, that would mean that I would star both sides of my equation, okay? And so if I'm going to star both sides of my equation, I'm going to get C star of S is equal to. And then here you apply the star transform to your leftmost, so G star of S, R star of S. And then you can write that in terms now of your Z domain. C of Z is equal to G of Z, R of Z. So that's perfect. everything works correctly. And so that's one property of the star transform. Now let's look at another variation where you might have C of S. C of S is equal to, and then here we have G of S, H of S times R star of S, okay? And say if you want to take the Z transform of both sides, Z transform here, Z transform here. Sorry, not the Z transform, the star transform on both sides. So what we get here is we get C star of S is equal to. Now, notice that the star transform is going to apply to both terms here. So what we have to do is, it's not like distributive, like it doesn't go to each term here. The star transform is going to go to both G and H. So it's going to go and apply to both, just so you know, so it would look like the following. It doesn't distribute to each individual. It distributes just to the leftmost of the one that doesn't have the star transform. So here we would see that it applies to both G and H, not each one individually. So that's why we had the bar. So you have to be careful with your star transform because it does apply to both terms on the left of the ones that aren't starred. It doesn't apply to just like each one independently. So that's why we represent the bar here. And so that's just some important properties of our star transform. And notice that if we were to take the Z transform of this, we'd get C of Z is equal to G, H, and then a Z, and then R of Z. And so just be familiar with that. You can go from the star transform straight to the Z representation. And so now that we see that, what we're going to do here, so we saw the property where you can basically just distribute here to get your G star of S and then R star of S and convert that over. What we're going to have in our example is, for instance, let's say we have the following system. So this system has our R of S, and then we have a sampler. And so this is our open loop system. So we have a sampler here, and then it's going to run through, and we're going to have our zero order hold. So that's going to be 1 minus e to negative st all over s, right? That's what your zero order hold block is. And then we're going to have our actual plant transfer function, which is 1 over s plus 1. And that's going to produce our output C of S here. And so if we need to actually find the unit step response, so find the unit step response. What we're going to have to do here is, in order to find our unit step response, we have to make two equations. A lot of times, when you have these equations, the first thing is, what I can tell you is you have to find an equation for the output, relating it basically to the output of the switch here. So you have to find your output in terms of the output of the switch over here. And then the other one is you usually write an equation for the input to the switch. But here we just have R of S for the input, so you know. So we're going to write the output equation, which is C of S, in terms of our output of the switch. So the output of the switch on this side would be R star of S. So you agree with me there? So right here, I'm going to represent everything. Remember, we typically represent the zero order hold in the plant transfer function as G of S here. And so I'm going to say that my G of S multiplied by my R star of S. And so what I'm going to do here is now I'm going to take the star transform on both sides. So I'm going to get C star of S is equal to G star of S, R star of S. And now that I got that, what I'm going to do is I'm going to take the Z transform. So I get C of Z is equal to G of Z times R of Z. So that's taking the Z transform. And now I'm going to have to represent and plug in what I actually have here. So I need to find what my R of Z is, and I need to find what my G of Z is. So they said it's the unit step for my input. So if we know the unit step, remember, R of T, if it's the unit step, is just UT. Converting this to the S domain, R of S is equal to 1 over S. And converting this to the Z domain, if you look at your Z transform table, it's going to just be Z over Z minus 1. Okay, so we found RZ. Now we need to find G of Z. So G of Z is more the difficult part. In order to find G of Z, what we're going to do is we're going to find G of S first, and then we get G star of S. And then from G star of S, we find G of Z. So what we're going to have is our G of S is equal to, and then here, right, it's just the combination of these two. So it's 1 minus e to negative st all over s multiplied by 1 over s plus 1. Now, what we have is we need to find G star of S now. So if you want to represent this, basically, just with one common denominator, it'd be S over S plus 1. And then here, what we'd have in here is this would be an S plus 1 multiplied by this. Sorry, if these were multiplied, then it'd just be 1 minus e to negative st. Okay, so now what we have to do here, knowing that we have, let's see, 1, because this would be s, and then 1 minus 1 negative st. Okay, yeah, that'd be our G of S term that we have within here. But notice, oh, wait. Remember I told you guys a trick real quick? When you have your G of Z, it's going to be equal to this term contributes to the 1 minus Z to negative 1, correct? And then you have to find the Z transform of your GP of S, which is 1 over S plus 1, and then multiplied by S. So S times S plus 1. Because remember what we said, going back to what we had over here, if you have this definition where you have your G of S is equal to, and we have it written out, this term up here is what's responsible for right here. Just plug in Z is equal to the ST. And so that's the easy Z transform, but you have to find the Z transform of your GP of S all over S. And so that's what I did here. I have my GP of S, 1 over S plus 1, and then in denominator, I also have that S. So now, what I have to do is, this is what I need to find a Z transform of. And so looking at this in particular, I'm going to have to solve for this to find a Z transform and then multiply it by 1 minus Z to negative 1. And so what we're going to see here is when I have to solve for this one in particular, we notice that our G star of S, just looking at this one right now, is going to be the summation, and then your pole occurs at 0 and negative 1. Okay, and then it's going to be multiplied by the residues of, and then what's your G lambda? It's going to be 1 over lambda times lambda plus 1 multiplied by 1 over 1 minus e negative t, and then s minus lambda. Okay, now that we have it in that format, what we have to do is solving for our G star of S here. We're going to get, particularly if we multiply by lambda, our first residue, and then 1 over lambda times lambda plus 1, and then 1 over 1 minus e to negative t, s minus lambda, and then evaluate it at lambda is equal to 0, plus, and then here we're going to have lambda plus 1, our other residue, because it's the summation of the residues, 1 over lambda times lambda plus 1, and then 1 over 1 minus e to negative t, and then s minus lambda evaluated at lambda is equal to negative 1. Okay, so what we're going to notice here is this lambda cancels this lambda here. Lambda plus 1 cancels lambda plus 1 here. Okay, now plugging in lambda is equal to 0, what we're going to get is we're going to get 1 over 1 minus e to negative ts plus, and then we're going to have here, it's going to be, actually it will turn into a minus because it's 1 over negative 1, and then it's going to be 1 over 1 minus e, and then to negative t s plus 1. Now that we have it in that format for G star of S, what we're going to have to do now is, remember, now we were finding this, only this part right here. That's what we got here. We just found the G star of S. So this was our G star of S. Taking the Z transform of this, what we're going to get is for GZ, I should probably just call this term, like if we're just solving in terms of that, something else, but our GZ is 1 over 1 minus z to negative 1 minus, and then here we're going to get 1 over 1. Looking at this in particular, it's going to be minus z, and then it'd be to negative 1. And then here, because we have e to the negative t, we would keep that down. So we'd also have e to negative t. And then if I'm going to multiply by z in the numerator and denominator, I'm going to get z over z minus 1 minus z all over z minus e to negative t. Now, what I have here basically is what I'm going to do is I'm going to then find this in terms of, I would say, because we're finding our g of z here, which is going to multiply by both. I think it would be helpful. Let's see if I have a z over z. If we get this in terms of the common denominator. So z minus 1 times z minus e to negative t. And then here we're going to have z multiplied by z minus e to negative t. And then here minus z times z minus 1. Okay. And so now what I'm going to do is looking at this in its entirety here, which we have here. So we just found the z transform right there of our function. And so now multiplying this by 1 minus z to the negative 1, all multiplied by z minus e to negative t minus z to the z minus 1, then all over, and then z minus 1 times z minus e to negative t. What you have to remember is we can represent this multiplied by z in numerator and denominator. What you're going to get is you're going to get z minus 1 all over and then z multiplied by z times z minus e to negative t, and then minus z minus 1, and then all over z minus 1, z minus e to the negative t. Okay. Now what we're going to notice is some terms are going to cancel. This z minus 1 is going to cancel with the denominator here. This z down here is going to cancel with the common z in our numerator. And so for our final result, we're going to get z minus e to the negative t multiplied by, minus z minus 1 all over. And then here in our denominator, we have z minus e to the negative t. Okay. Now, basically, what we have here is we finally got our g of z, which is great. We finally got g of z. Now, what we have to do is, remember, this is only g of z, but we wanted to find a unit step response, which this is talking about c of z, correct? Or technically c of z, but really we need to find it in terms of the time domain, so c of kt. And so, we found our g of z here. Knowing our g of z, we need to calculate our actual step response. So going from up here, we're going to then get our c of z is equal to, remember, it's going to be your transfer, so g of z, your transfer function multiplied by your input, rz. So plugging those in, what we got is z minus e to negative t minus z minus 1 all over z minus e to negative t. And then what is our rz? Remember, we calculated that. It was z over z minus 1. So now with that, what we're going to do here is trying to find that. What we can try and do is looking at what we have here, c minus e negative t minus c minus 1. Okay, I'm trying to think what might be. Okay, we can simplify this because we have a z minus c, correct? In our numerator, so a z minus a z is going to be 0. And then we would have 1 minus e to negative t all over z minus e to negative t times z over z minus 1. Okay, that's what I get here. So looking at Now we would have to take the Z transform, the inverse Z transform, in order to calculate what our time domain version would be. So having to take the inverse Z transform of this, what we're going to get in particular is then we have to separate this in terms of two partial fractions. So what we're going to have here is we're going to do our C of Z all over Z is equal to. And then so what we're going to have is we're going to get C of Z all over Z. If this is our C of Z right here, and if we divide by Z, what we're going to get is this term would cancel, right? We wouldn't have this Z. And so we're going to have 1 minus e to negative t, and then it would be multiplied by z minus e negative t times z minus 1, okay? And then splitting that up into 2, you're going to get a over z minus e negative t plus b all over z minus 1, okay? Now, what we have to do is looking at this, we're going to have to solve for a and b. So a is equal to, it's going to be z minus e to negative t, and then c of z all over z. Plugging in for z is equal to e to the negative t, okay? So now solving for this, what we're going to get is we're going to get 1 minus e to negative t all over z minus 1, plugging in for z is equal to e to the t. And so then what we're going to get here is we're going to get 1 minus e to negative t all over, and then here we're going to get et minus 1. Now, what we're going to get for our b term is our b is going to equal, and then it's going to be z minus 1, c of z all over z, and then plugging in for z is equal to 1. What we're going to get here is c of z over z is right here, so multiplying by z minus 1. And so we're going to get 1 minus e to negative t all over, and then it's going to be 1 minus e to negative t, which is just equal to 1, correct? Here, what we're going to notice is, notice if I multiply by -1 in my denominator, say if I pull out, here, if I did 1 minus e negative t all over, then pulled out a negative, I get 1 minus e negative t. So I get a -1 here. So for my A, I got -1. For my B, I got +1. So my C of Z all over Z is equal to, up here I get a -1 over Z minus E negative t. And then for B, I get +1 all over Z minus 1. Solving for my C of Z, I get -Z all over Z minus E to negative t plus Z all over Z minus 1. Now, taking the inverse Z transform of this, what we have to do is we have to then replace, if you recall from your, you actually have a table, correct? Where was it? I have it right here. Our table here, this is Z over Z minus 1. And notice that this is the constant, which for us, it's just going to be your unit step, correct? So this is just our unit step here. This is your U of t. What about this term right here? Looking at my Z transform table, I need to find a Z over Z minus e to the negative t, where my A is just 1 here. So that's going to be e to the negative at, which for us, the A is just 1. So it's just going to be e to the negative t. So this would be e to negative t, but remember the negative sign in front, so it's just minus e negative t, ut plus, and then ut. So that's my C of t. And so this is technically 1 minus e to negative t ut. That's my C of t. But then remember, this is your C of t, but recall that this is fictitious, what we said like in our you normally represent it in terms of C of k capital T, which is 1 minus e to negative k capital T, and then u of kt. Because what you're going to notice is that we really found C star T, like we're defining this because we started with samples. We're defining this in terms of our samples, not in terms of continuous time, because we're not for sure if in between those samples that this is correct. So a lot of times we represent this in terms of capital KT. So this would be your C of KT that we'd have here. So that's how we derived the entire unit step response. For there is we just started out with our open loop transfer function. We found our G, we wrote an equation for the output in terms of what's after the switch. And then we found the C star of S. For the C star of S, we were going to have to find our G star of S. And so knowing that our G of S, we could find it. We know in order to find a G of Z, you just have to take 1 minus Z to -1. And then you have to do your plant transfer function over S. And then we found what our G of Z was. And then multiplying that by RZ, we're able to solve for Z is C of Z. Then taking the inverse C transform, we can get our C of T. But remember, that's fictitious. We can only really write it in terms of K capital T, because based on our sampling time, that's going to impact our resolution at the output. So that's why we substituted in for T, capital K capital T. Okay. Now that we have that, what we're going to do is now we're going to specifically define two parameters that I think are really important for you guys to know. So the first one is going to be our DC gain of the system. So the DC gain is going to be equal to the limit as Z approaches 1 G of Z. So that's literally just plugging in for your G1. And so that is really important when you have your DC gain. And then the final value, like your final value theorem, for the final value or steady state that's often referred to of your C of KT or C of KT, what you're going to get is your C of SS, which just represents your steady state of your output, is going to be equal to, the limit as K approaches infinity. So your infinity sample, so that means like at the very end sample, your C of KT is going to equal the limit as Z approaches 1, and then it's Z minus 1 C of Z, which is also equivalent to saying what we have in here is you can say this for your open loop transfer function, so I'm a little nervous to write it. Just don't confuse it with your closed loop. It's Z minus 1 G of Z times RZ. This would be for your open loop transfer function, your G of Z. Just be careful for your closed loop transfer function. This would be T closed loop with Z. But I would stick to these two general definitions for your DC gain and also for your steady state value. So here's your DC gain here. In your steady state value, I would make sure just to write that down. This is true for your open loop transfer function, but remember for your closed loop, you'd have to plug in T close. So I'm just a little worried if you wrote that down. Just remember your C of Z is equal to your transfer function multiplied by your input. Okay. So now that we talked about that, what we're going to see is we're going to look at 3 different configurations here. And then we're going to define specifically our systems for these. And so let's look at how these are formulated. So we're first going to try and define the system output for the following. So find the system output. So we're given the following block diagram where we have our E of S, and then we have a sampler, and then it enters in our G1 of S, and then we go to A of S, and then it gets sampled, then we get A star of S, and then it goes to our G2 of S, and then it goes to our C of S at the output. So what we're going to get here is this is our E star of S. So remember, if we have to find the output, remember I said you make the output in terms of the input to, you write the output in terms of the output of the switch, and you write an equation for the input to a switch. So right here, we're writing the output in terms of the output of the switch. So we'd have our G2 of S multiplied by A star of S. And then we're going to write an equation for the input to a switch. So A of S is equal to, and then G1 of S times E star of S. So those are two equations. You form one for your output in terms of the output of a switch, and you form another equation for the input to a switch in terms of what you have coming at the output of another switch. And so that's what we have here. And now I'm going to take the star transform of these. So notice I need the star transform of A to solve for my output. So I'm going to take the star transform. So down here, my star transform of A is going to equal G1 star of S times E star of S. Plugging that now in for my C star of S, when I solve for C star of S, it's going to equal G2 star of S times A star of S. So taking a star transform both sides, plugging in for my A star of S, what I got is I'm going to get C star of S is equal to G2 star of S times G1 star of S times E star of S. Now, what I have, this is my system output. If you're literally just to take the Z transform of this, you get CZ is equal to G2Z, G1 is Z, E is Z. So now we got the output in terms of the Z transform. So here I'm just going to leave it in terms of the Z transform. So we have it. And now what we're going to do is we're going to find for our second configuration, say that we have E of S, and then it goes through a sampler here, and then it's going to go in, remember, this is the sampled output, so E star of S, and then we have our G1 of S block, and then we're going to go through, get our G2 of S, and then we're finally going to have our output C of S. Okay, so we need to find an equation in terms of the output, right? So our output is pulse transfer function would be that sandwich between C of Z and E of Z. Right here, C of Z, and the pulse transfer function would be defined as what we have here. Sorry, like a different color. So this would be referred to if he asks for the pulse transfer function, that is the following right here. So this is the pulse transfer function, right? Because that's your transfer function of your system that is pulsed, where the following, this is referred to as the discrete, because now it's in the Z domain. So this is your discrete transfer function, because your input is just the E term, but everything else is your transfer function. So this is your discrete transfer function. Hopefully that makes sense, because it's in the discrete domain for Z, while the other one is still in the S domain. Okay. Now that we have that, what we have to do here is remember, we form our output in terms of the output of the switch. So writing equation for the output in terms of the output of the switch, we'll get G2 of S, G1 of S, and then we're going to have E star of S. Okay. And then for the, remember last time we formed an equation for the input to the switch, but here there's nothing that comes before this input. So E of S would just be equal to E of S, so it's not really that helpful. So here, now looking at what we have to do is if we take the star transform of both sides, remember when I apply the star transform here, so it's going to apply to everything that's not starred on the left. So I'm going to get C star of S is equal to, and then I'm going to get G2, G1, both of them will be starred. And then E star of S, okay? And then taking the Z transform of this, we're going to get C of Z is equal to G2, G1, and then this is going to be a Z, and then E of Z. And so this would be my pulse transfer function right here, where this right here is going to be my discrete transfer function right below, right here. So that's what I have. And then for my last one, what we're going to have, so this would be my solution for finding the output in terms of my transfer function and input. Now, for this block diagram configuration, we're going to have E of S, and then it's going to go through our transfer function block, G1 of S, then we're going to get A of S here. So our A of S, and then at the output, it's going to be A star of S, then G2 of S, then we're going to have C of S as our output, okay? So what we're gonna have here is we're gonna have our output. We need to write it in terms of the output of the switch. So now you're getting pretty familiar with why we write these equations, is equal to G2 of S times A star of S. Now, we need to form an equation for the input to the switch, and notice that stuff comes before it. So A of S is equal to G1 of S times E of S. Now, what we're going to have here is we're going to have, taking the star transform, A star of S is equal to G1 star of S times E. Oh, oops. Because remember, if we have to take the star transform of both sides, it's going to apply now to, what we're going to see here is it's going to apply to both terms. So we're going to have G1 times E star of S. And remember, it applies to both, so you have to put like that bar right above it. And then now, what we're going to have here is plugging this in for our output, we're going to get C star of S is equal to, and then G2 star of S. And then our A star of S, that's G1E, and then bar star of S. Now what we're going to have for C of Z is equal to, and then we're going to have G2 of Z, G1 E of Z, and then this has a bar. So the issue here is that this would not be doable. You can't make your input, this is wrong right here. The reason this is wrong is because notice that your input is a part of your transfer function. It's not separate. Your input has to be separate. When you plug in different inputs, your input shouldn't be dependent upon your transfer function here. It has to be separate. Like here, we have our input separated from our transfer function, input separated. Here, your input shouldn't be dependent upon your transfer function. They should be independent of one another. So this would be wrong because you cannot find the transfer function. Your transfer function would always be dependent upon your input. So cannot find your transfer function because it's attached to the input. So your transfer function is always changing, and that is not correct. Your transfer function should remain constant. It's your input that's changing. So your transfer function is dependent upon your input, which is wrong. So you're going to need, what this is telling you is you need a switch always at the beginning of your input signal. And so that's what we saw here. Now that we did that, what we're going to notice is looking at our systems, we're going to have to develop now. For our next one, we're going to look at when we do apply a switch there, what's going to particularly happen when we have our filter. So now we were looking pretty much without the filter effect, but when we apply one, what we're going to notice is it's going to operate in a little different of a manner. So here, if we have, for our example, say we have an input, which is R of S. And then we have an analog to digital converter. Remember, because we just said we need a switch always at the input in order to convert it. So we're going to have an analog to digital converter. Then we're going to pass through our filter. So the filter are, I like to call it always, for mine, I call it DZ, but here they call it HZ. But usually it's called by DZ for the filter. And then we go our digital to analog. And then we're going to finally go through our plant transfer function to get our output. And then our output is going to be C of S. Remember, in controls, it's usually C of S. So now what we're going to have here is looking at what we're going to have is at this point, it would be R star of S, right? If we're just labeling it. And then here, what they define this point as is they define it as N star of S. Okay, so they say we need to find the output. And so this is C of T is our output to a unit step, which is usually for ours, for our instance, that would just mean R of S is equal to 1 over S, right? So R of S would equal to 1 over S. Our input would just be the unit step. And so the filter they gave us, the filter is described by, so they actually gave us an equation. M of K is equal to 2R of K minus R of K minus 1, okay? So they gave us an equation describing the filter. So what we have to do is, looking at this, we're going to have to find what our filter is in particular. Because if we're going to make an equation, remember what this looks like is we have our R of S, then we have like a sampler here. That's what our A to D is. And then that's going to make our R star of S. And then it's going to go through our filter, which is H of Z. And then it's going to produce our, here we have M star of S. And then it's going to have our zero order hold. So this is really just your zero order hold, your digital to analog block. And then it's going to go for your plant transfer function 1 over S plus 1. And then it's finally going to go to your output. So defining the equations that we're going to need here, remember, you usually combine the two up here. You combine your zero order hold with your plant transfer function to make your G of Z here. And so if we know our G of Z, and then, or you can call this G of S for now if you want, G of S, and then multiplied by our input here, then we can describe this one. And then if we find out what our actual filter is, then multiply that by here, then we can find our output, because our output's going to be our G of S times our M star of S times our H of Z times the R star of S. But here, what we're going to do first is we're going to have to find everything in terms of the Z domain. So if we find this in terms of Z domain, we find this in terms of the Z domain, and this in terms of the Z domain, we can multiply all of them together to get our output, because the only issue is our filters in the Z domain here. So trying to find our filter now in terms of the actual domain. So remember, H of Z is going to equal M of Z over RZ, right? Because it's the output over the input. So what we're going to have here is our H of Z is defined as our output, M of Z over our input. Looking at this equation here, taking the Z transform of it, so taking the Z transform of this equation, I get M of Z is equal to 2, and then this would be RZ minus Z to negative 1 R of Z, okay? So now output over the input, so M of Z over R of Z is going to equal. What we're going to get here is we're going to get specifically 2 minus Z to the negative 1. Now, what we found is we found our H of Z, correct? And so with our H of Z, what we're going to have to do here is, now that we found this, what we're going to have to find is we know what our RZ is, correct? You know, our RZ is literally just going to be Z over Z minus 1, because it's a unit step. So we know what our RZ is. And then we know, so our input here, then we would know, so let me write it real quick. We know the input RZ is equal to Z over Z minus 1, correct? So we know R of Z. So we know at this point what RZ is. We know H of Z. This is just a signal, not a system. Then we just need to find G of Z, and that will give us our C of Z, correct? So that's what we need to find, because our C of Z is just going to equal our G of Z multiplied by our H of Z multiplied by RZ. And so now, in order to find G of Z, what we're going to have to do is we're going to have to use, this is a zero order hold, and then it goes through for a plant transfer function. So remember, for the zero order hold, you can write it 1 minus Z to negative 1, and then it's just going to be the Z transform of your plant transfer function all over S. Okay. So in order to find this right now, our plant transfer function, if we're looking at our G star of S, it's going to equal. What we have here is it's going to be 1 over S times S plus 1. So remember, you do the sum of the residues. So our residue is going to be at lambda's equal to 0 and lambda's equal to negative 1. Then it's going to be residues of, and then our G lambda is going to be our 1 over S and then S plus 1, because here, that's what we have in here. If you write this out, literally, this part right here, remember, if you plug in your GP of S, you're going to get 1 over S times S plus 1. Is the S plus 1 here, and then remember the S down there. So s times s plus 1. And then what we're going to have in here is, remember, it's 1 over 1 minus e to negative t, s minus lambda. Okay, now that we have that here, what we're going to have to do is we're going to have to find our g lambda. So finding this in terms of lambda isn't hard. Remember, if this is our term, just putting it in terms of lambda, you're going to get 1 over lambda times lambda plus 1. Okay, now what we're going to have to do is evaluating at the first residue at lambda equal to 0. So lambda times 1 over lambda times lambda plus 1 multiplied by 1 over 1 minus e negative t, and then s minus lambda for lambda equal to 0 plus, and then it's going to be lambda plus 1 over lambda times lambda plus 1, and then 1 over 1 minus e negative t, and then s minus lambda for lambda equal to negative 1. Okay, so lambdas can cancel lambda, and we're going to get lambda plus 1 cancel out. So now plugging in lambda equal to 0, we're going to get 1 over 1 minus e to the negative t s. Okay, plugging in the other one for negative 1, we're going to get minus. Then here we're going to get, because that'd be 1 over negative 1, so negative in front, 1 over 1 minus e negative t, and then s plus lambda. And so remember our s minus lambda, it's going to be negative 1, so it's s plus 1. So that's what we get here. So this is solving in terms of our g star of s, which is great. But now we need to find the z transform of that. So g of z is equal to, and so for this part right here, we're finding the g of z. So it's 1 over 1 minus z to negative 1 minus 1 over, and then 1 minus z to negative 1 e to the negative t. Okay, now finding it in terms multiplying by z, numerator and denominator, we're going to get the following for gz. So that's great. So now we found this part right here. That was what we got. We got the z transform of this. Now multiplying in front here. So we're going to get our g of z is equal to 1 minus z to negative 1. And then here we have our z over z minus 1 minus z all over z minus e to negative t. Now, remember, you can represent this in terms of z minus 1 over z all over z minus 1 minus z all over z minus e to negative t. And you're going to notice that what's going to happen is the z's will cancel. And then we're going to see when we individually do this, we're going to get multiplying z minus 1 over this term, you're going to get a 1 minus, and then here we're going to get z minus 1 all over z minus e to negative t. And then if we reduce this, you're going to particularly see making common denominator z minus e to negative t. We're going to get in our numerator here, we're going to get a z minus z, so that would cancel, and then you would get 1 minus e to negative t. And so that's what we're going to have here. And so now that we found our c of z, our g of z here, we got our g of z finally, we're going to have to plug that in for c of z. So recall from here, your c of z is going to equal your g of z. So I'm going to write it right here. Your c of z above is going to equal your g of z multiplied by your h of z multiplied by your r of z, right? And so because this is just a signal right here, it's not a system. And so our signal begins at our, the input right here multiplied by the transfer function multiplied by our transfer function is equal to our output. And so what we're going to notice here is writing our c of z in terms of what we got. So remember, our input was just the unit step. So it was z over z minus 1. Okay, now what our h of z was, what we solved for is our h of z was 2 minus z to the negative 1, which if we're writing that in terms of just 2z minus 1 all over z. So it's in the same. So it would be 2z minus 1 all over z. And then what was our transfer function here, g of z? Our g of z was 1 minus e to negative t all over. And then here we have z minus e to negative t. Cool. Now we got the output in terms of our input signal, RZ, our filter, H of Z, and our G of Z. What we're going to do now is having to solve for this. We're going to notice that the Z's will cancel here, Z with Z. And now we're left with the following. So simplifying, get 2 of Z minus 1 multiplied by 1 minus E to negative T all over Z minus 1, Z minus E to negative T. Cool. Now what we have to do in order to solve this system is we have to do partial fraction decomposition in order to get C of T. So what I'm going to do here is we're going to take out, remember when you do partial fraction decomp, it's going to be CZ over Z is equal to. And then here we're going to have 2Z minus 1, and then 1 minus E to negative T. And in my denominator, I don't have any Z in the numerator, so it's going to be Z multiplied by Z minus 1 multiplied by Z minus E to negative T. Splitting this up into 3. We're going to have A, B, and C. So what we have to do is we have to solve for A, B, and C. So getting our A is going to equal Z multiplied by CZ over Z, where Z is equal to 0. Okay, so what we're going to have here is multiplying by Z and plugging in 0. What we're going to find for A in particular is that it's going to be, if we plug in here 0, we're going to get -1, and then times 1 minus E to the negative T, and then all over, and then it's going to be -1 times negative E to negative T, so that would be a positive E to the T in the denominator. And so then here, let me just write that out. -1 multiplied by, and then 1 minus E to negative T, all over, and then plugging in 0 here, I would get -1 times negative E to negative T. So here would cancel here. And then what we're going to see is that would be, if we have here, we would get particularly, this would be in the denominator. So we would bring that up and we would get negative, let's see, 1 minus E to negative T divided by this. We're going to get 1 divided by, oh yeah, we can just write this out as separate. So you could just write this as 1 divided by, and then negative E to negative T, and then minus E to negative T divided by minus E to negative T. And then you're going to get here, this would be a 1 because this would be E to negative T divided by E negative T. So that's a 1, and then minus, and then so that'd be in, if we bring this to the numerator, it'd be E to the positive T. And so then it would be 1 minus E to the positive T. That's what you would get. And then solving for B, you would get Z minus 1, C of Z all over Z. And then plugging in Z is equal to 1, you're going to get, here we would have, let's see, if you multiply by this, you get 2 minus 1, so you get 1. And then here plugging in, it'd just be 1 minus E to negative T. And then you're going to have, here in your denominator, this would just be 1. Then you'd have 1 minus E to negative T. Oh, that's nice. Then these two cancel. And then you're just left with 1. So that one's nice. And then the C is equal to Z minus E to negative T, and then C is Z all over Z. Remember, you're plugging in for Z is equal to E to positive, Z is equal to E to negative T. And so what we're going to get here is what we're going to have is plugging that into our equation, we're going to get 2E to the negative T minus 1 multiplied by 1 minus E negative T, and then all over. Here we're going to get E to negative T multiplied by E negative T minus 1. And then we're going to have here, what's going to happen is if you take out a negative, so if I took out a negative here, this would become a positive 1 and a minus, so then that would cancel here. And then I'm going to have, here, if you separate it into 2, you would get a -2, and then you would get e to the positive t. And so this would be a -2 and then plus e to the positive t. And so now I solve for my a, b, and c. Plugging those into my equation, I'm going to get c of z over z is equal to, my a was 1 minus e to -t all over and then z. My b was 1 all over z minus 1. And my c was e to the t minus 2 all over z minus e to the -t. Now that I got that, solving for my c, the z, you're going to get 1 minus e to -t, and then plus z all over z minus 1, and then plus, and then here e to t minus 2, z all over, then z minus e to -t. Okay, cool. So what we're going to have to do now is taking the inverse z transform of this. So what we're going to see particularly, in order to get the inverse z transform, or CT, you have to use your table. So that's why I said make sure to include it on your cheat sheet or else you're screwed. Not gonna lie. So your CT, it's 1. So looking at our 1, if you notice, the only thing is like this delta function it says here. So what this means is basically your delta at time 0 is 1. That's what it's trying to say. So here what we're going to notice in particular is that this is a constant all here, right? This is just our constant. This is just our constant term right here. It's not dependent upon z at all. And so what this is going to be is in our constant, it's the same constant 1, but it's multiplied by the delta function at time 0. So we're going to get here the same constant 1 minus e to -t, but it's just multiplied by the delta function at time 0. And then z over z minus 1, that is right here, z over z minus 1, and that's our u of t, because that's just the constant starting at time 0. So plus u of t. And then here, what we're going to have specifically for our 1 right here, you're going to notice we have an e to the t minus 2. This is just a constant times z over z minus e to -t. So this would be my z over z minus e to the -at. So you get e to -at where my a is just equal to 1. And so this would be plus, and then so my constant's in front, e to the t minus 2. And then it's going to be e to -t, and then multiplied by our u of t. E to -t multiplied by t. Okay, now that we had that there, we're going to have to, oh, sorry, this is, sorry, continuous time t. What we're going to do is plugging in, remember, this is fictitious. We have to say, because technically we're in terms of the discrete domain, so we can't represent it fully in terms of the continuous domain, depending upon our sampling. So depending upon our sampling, our reconstruction, you have to plug in for lowercase t, capital, or k, capital T. So we're going to get 1 minus e to negative, that's a capital T still, so it stays the same, plus, and then u of kt, and then plus e to t minus 2, and then e to -kt, and then u of kt. Okay, and so that's what we have here for our output. So that's how we solved for it, using what we know. Okay, now that we've found that for our system, what we're going to do now is we're going to look at a closed loop system. So we're dealing all with open loop systems. So in order to find the closed loop system, say that we're given the following configuration, where we have our R of S, then it goes through a summing block here. And so in our summing block, it's going to have a positive and a negative here. And then what we're going to see is that this is, of course, your error signal. And then it's going to go through sample, because we have our analog to digital converter. And then it's going to go through our transfer function. So this would be like your error signal E of S, and you'd have your E star of S here. And then it's going to go through your transfer function, so whatever your G of S is here. And then it's going to go create your feedback path here, which is H of S. Remember, your sensor is in the real time domain. And then it feeds back in. So this is your output here, C of S. Okay, so what we're gonna have to do is we have to find an equation for the output in terms of the output of the switch. So remember, C of S is equal to, and then we have our G of S multiplied by E star of S. So we made an equation for the output in terms of the output of the switch. Now we have to make an equation for the input switch because it's not E of S is equal to E of S, it's E of S is equal to R of S minus H of S times C of S. And so what we're gonna see here is our E of S is gonna equal R of S minus, and then here we have our C of S multiplied by H of S. Okay, so what we're going to have here is looking at this in part. Actually, what you're supposed to do, rule of thumb, sorry, it's your transfer function, then your input. So I'm going to write it actually in terms of H of S and then C of S, just so we stay consistent because that will make it easier in the math. Okay, so in order to, so let me just rewrite that, sorry. So H of S and then C of S. So what we have to do is first, remember your output, you have to find E star of S. So taking the star transform on both sides of this equation, what are we going to get? Star transform, star transform. So I'm going to see for my E star of S, it's going to equal R star of S minus. Then here, I'm going to get H and then C combined star of S. Okay. Then I'm going to have here for my C of S, plugging that into my equation, what we're going to see in particular for this one is it's going to be very interesting. Let me see. Wait, if we do that and then we solve in terms of our E of S is equal to, wait real quick, because what I notice is if we plug in our G, okay, give me a sec real quick. Made a slight thing here, E star of S, yeah, okay. Undo that star transform I told you to take originally. Okay, so let me just rewrite that equation right there. That was a bad one. So E of S is equal to, and then we have our R of S minus, and then we have our H of S, C of S. Well, we know our C of S is equal to this, right? And so if we want to solve for E of S, so we get rid of the output. So when we plug it in here, it's not in terms of the output on both sides. So we find E of S in terms of R of S minus H of S. And then we know C of S is just equal G of S times, and then E star of S, correct? And so now what we have to do is solving in terms of our E of S. If we take the star transform of both sides, now what we're going to see is taking the star transform here and taking the star transform here. We're going to get E star of S is equal to, and then this is R star of S minus, and then it's HG combined star of S, E star of S. Okay, so cool. We got that, and now we're solving for E star of S. E star of S is going to equal, and then here, we're going to have our R star of S solving just on the other side. If you move this plus HG star of S, you get over 1 plus HG combined star of S. Okay, now that we got that here, what we're going to do is we're going to plug in our E star of S to get our output now, just transfer function times the input signal. And so what we're going to see here is if we plug this into here, what you're particularly going to get is G of S multiplied by R of star of S all over 1 plus HG star of S. Okay, this is great, but we want to represent our output in terms of Z. So this is going to be G of Z, now, this is our output, right? C of S. So you have to take the star transform of both sides. So taking the star transform or both sides here, what we're going to get is you'd have then your G star of S, right? And then the E star of S would stay the same because it only applies the left-hand term. So your C of Z, which is the star transform, is going to equal your G star of S. And so our G star of S would just be your G of Z multiplied by RZ all over, so this would be RZ, 1 plus HG, and then a Z, and this is combined. So there's your transfer function of your closed loop system. So the important thing just to take away from here is that you have two different ones. You have the transfer function of the open loop system. And so what we define that as is it was just T of Z is equal to G of Z times H of Z. But we had the transfer function of the closed loop system. And what we saw for this one is for this type of configuration here, is for a closed loop system, our T of Z is equal to G of Z all over 1 plus H G of Z. Let's see if I have white out real quick. H G of Z. And that's combined, okay? So that's the big thing. You just got to know the difference here. Our open loop system, we saw it's GZ times HZ, but for our closed loop transfer function, we see that's GZ over 1 plus HG combined of Z. And so that's what we have here. We just noticed for those two different ones, it's not like our normal one in the S domain where it's H of S times G of S. This one is combined. So just know those two differences and how we derived it. I would say it only works though for this configuration. So say if the sampler was put over here, then you might get a different type of system. It really depends on what you have. So I would just derive it if it's not in this format to make sure that you write the output in terms of the output of the switch, and then you write the input to the switch in terms of your other terms here, and then just find the transfer function, because just in case he gives you a different format that is not this type of system format, just solve for your system, get the transfer function, make sure there's no errors there. And so now that we saw that, what we're going to do is we're going to, okay, this is a good example where the transfer function is not the same. So we're going to try solving a closed loop system, and you're going to see that it gives us a different output. And so here, what we're going to have is we're going to have to find the output just like we did, but our switch is going to be moved. So what we're going to have is we're going to have our RVS. Then we're going to have it coming into a summing block. So here it's coming in and then minus here because it's feedback. And then this is our E of S. And then we have our transfer function, G of S. Then it goes to the output C of S, okay? And then we have a sampler here. And then it's H of S. And then what we're going to have is, so this is our sampler. Every time T, it's going to sample. So what we're going to do is we need to find C of S. So let's make our equations. So our C of S is equal to, what is it going to be? It's going to be basically our transfer function G of S. And then it's going to be times E of S, right? Our signal coming in. And then we're going to have, well, what's our E of S defined as? E of S is going to equal R of S minus, and then it's going to be our H of S. And then at this point, isn't this C star of S if I'm to label it? So C star of S. Okay, now we want to find the error signal, not in terms of the output. We only want E of S in terms of like E of S, R of S, H of S, because we're going to plug it in here to find what our output is. And so looking at our C star of S, if you're going to take the star transform of both sides, plugging that in for E of S here, it's going to be R of S minus, and then H of S. Then plugging in our C star of S, it's just going to be G E star. Real quick, let's see. C of S is equal to, and then plugging this in, we're going to see that we get, wait, let me see real quick. C of S is equal to G. This would be, oh, wait, but then I guess the output of the switch, you're going to have to write, oh, remember what I said, guys? Write your output in terms of the output of the switch, which is technically here. So writing our output, because this is not, there's no switch here. So that's why you can't write it in terms of E of S. So C of S is equal to G of S. and then it's going to be multiplied by, and then, well, what's here? What's our signal coming in? R of S minus, and then H of S multiplied by C star of S. So our output is written in terms of the output of the switch. And so then our C star of S is just gonna be then, the input to the switch is just C of S, and you're solving for that, so we don't need write for the input to switch. Now, what we have to do from this equation is we're gonna have to then find the Z transform of it. So looking at what we're gonna get here, we're gonna get C of S is going to equal G of S, R of S, minus G of S, H of S, C star of S. Okay, taking the star transform of both sides of our equation, what we're going to get is we're going to have C star of S equal G R star of S minus G H star of S multiplied by C star of S. And so what we're going to get here is, now taking the Z transform, you're going to get C of Z is equal to GR of Z minus GH of Z, and then C of Z. Okay, so now that we got that, what we're going to see particularly is moving this over to the other side, you're going to get C of Z plus, and then this would be GH of Z, C of Z, and then we're going to have is equal to GR of Z. Now, solving for C of Z, it's going to equal GR of Z all over 1 plus GH of Z. Okay, so that's what we get here. So what we're going to see is we can't place this here because notice that our transfer function is connected to our input. So this is wrong because you can't have the transfer function as part combined with the input. They have to be separate of each other. The transfer function has to be independent, which we have here. Notice that our transfer function is independent of the input, where here it's combined with the input. So this would not be correct, but it's a really good example of showing you how to derive like a closed loop system if you're not given like the proper, like with the sampler here, and you have to find like the equation for everything, because you might be given one of those. So now that we saw that within our system, we're going to look at one last example for the closed loop systems, and then we're going to get on. So what we're going to have here is for the following. Say that we're given our R of S, and it goes through to a summing block here where we have feedback. And so this is going to be our sampler right here, our analog to digital converter. And at this point, it's E of S, right? But afterwards, it's E star of S. Then it's going to go through to our digital controller. So I like to represent it with DZ. So here I'm going to write DZ. Then we're going to go through to our zero order hold. So 1 minus E to negative TS all over S. Then we're going to go through to our plant transfer function, which is just going to be GP of S. And our GP of S, it's just going to not be defined for this specific example. So it's just GP of S. Then it's just going to go through to our output, C of S. Okay. And so from our C of S, it's going to go back. We're going to have our H of S here. And then it's going to feed back to our system. Okay. So what we're going to have here for a design is we need to find the output. And so we need to find C of S. That's what they want. So find the output. Output C of S. So what we're going to do is, remember, this is our transfer function. So if we define this right here as our G of Z, what we have within here, so G of Z multiplied by D of Z multiplied by E star of S, in which this would become then E of Z, then we could get C of Z, right? So for a system, we need to define equations first. So remember, define the output in terms of the output of the switch. So here we're going to have G of S multiplied by, and then this would be our, what we're going to see here is it would be T star of S multiplied by E star of S. Okay, this would become our, D star of S because we're writing it in terms of SD star of S times and then E star of S. Then we would have to write an equation for the input to the switch in terms of our input to the switch. So we would just write E of S in terms of the output. So it'd be R of S minus and then H of S and then C of S. Okay, so that's what we have here. So what we have to do is we know specifically what our C of S is. So plugging that into our equation, we're going to see that our E of S is going to equal R of S minus H of S multiplied all by G of S and then D star of S, then E star of S. Okay, so that's cool and everything. So having to then take, let's see, if we multiply that out, then that'd just be H of S times G of S times D star of S times E star of S. And so what we're going to see here is then when we need to solve specifically for our system here, we're going to notice that taking the star transform of both sides, what you're going to get is you're going to get E star of S is equal to R star of S minus, and then this would be HG combine star of S times D star of S times E star of S. Okay. Notice that when you take the star transform of both sides, you'd apply it to terms that aren't star transform and combine them together, and then the terms that already are star transform aren't affected. And now, what we're going to have to do is solving for your E star of S here. It's going to equal R star of S all over 1 plus HG star of S. And then this would be D star of S. Okay. Now that we have that here, what we're going to do is putting this term in terms. So we can straight up plug that into here in order to get what we want. So we can get our C of S is equal to G of S times our D star of S, and then multiplied by our R star of S all over. And then here, what we get in our denominator is 1 plus HG star of S times D star of S. And so what we're going to get here is now we're going to have our taking, because now we got it written in terms of C of S. So like technically that's correct for the output, but just so you see it in the Z domain in case, it would just be G of Z multiplied by, sorry, wait. If we were to take, oh, sorry, because remember, if you want to write it in terms of the Z transform, you have to take the star transform of both sides. And so then what we're going to see is then when you take the star transform of both sides, what we're going to get in particular is here. So applying the star transform, so we could get C of Z. So now it's going to be G star Z times D of Z. And then this is already in the star so this side is all star transform. It's just this term is the only term that's not star transform. So when we take the star transform, we would get G of Z and then times D of Z and then times R of Z and then 1 plus, and then it's going to be HG combine the Z and then D of Z. There you go. So that would be your output in terms of your input multiplied by the transfer function. So that would be in the Z domain, but if you had to find the C of S, it would be all this without the red star transforms. So that would be your correct one in order to solve that system. So hopefully that makes sense. Now that we saw that, what we have to do is looking after our closed loop systems, what we ran into was the time domain characteristics. So getting into those now, what we're going to see for the time responses, it's very similar to like our S domain, like our first order transfer functions and everything. but we just have to review that so we're familiar with how that works. Okay, so remember in your so now getting away from the Z transforms for a while and sort of hopping into our time domain stuff, we need to look at our first order systems and how those behave. So remember for our first order systems that they are written in the following format. We have like a G of S is equal to. So this is for first order systems. So first order systems. G of S is equal to. We usually have K over tau of S plus 1, where this K represents the final value. Tau is the rise time to get to 63% of the final value. And then, but oftentimes we're given it in the following format. B is equal to, and then all over S plus A. And so here, if you divide by A on both sides, you're going to get B over A is equal to 1 over A of S plus 1. And so what you can see is just our K is equal to B over A, and our tau is equal to 1 over A. And so that's what we see here. So just make note of that because it will pop up later. And so what we're going to notice is that for your first order systems, they're generally in the following, where you'll see like the response graph is that in our actual response, this is the final value here. So that's your K, your final value. And in order to get to 63%, that's your tau value to get to like 63%. And so that's what we're going to have here. And so now that we saw that, in order for your settling time for your first order systems, remember settling time is equal to 4 tau, and your rise time is equal to 2.2 tau about. Okay, I don't know why. There we go. 4 tau and then 2.2 tau. So that's your settling time and your rise time. And remember, your tau is just 63% of your final value, so 0.63 of K. Okay, now that we saw that, what we're going to have to do is we're going to look at one of the systems in the time domain and then do the equivalent in the Z domain, so it makes sense. So when we're dealing with a first order system, say that our G of S is equal to, and then here we have 4 over S plus 2. So it says that we need to find a unit step response. And so if we're given, like, say our block diagram is like this, R of S, and then we have a summing block. And then we have our E of S, and then we have G of S here. And then we have our output C of S. So if we need to find the unit step response, what we're going to do. So find unit step response. What we need to do here is that we need to find our C of T, right? You know, that's what our unit step response is, C of T. So what we have to do is, looking specifically at our system, we're going to notice that, well, how would you find C of S? This is just a simple transfer function, right? C of S is equal to, and then it's going to be G of S all over 1 plus G of S times, and then what's your input here? It's R of S. Okay, so what I'm going to get here is my G of S is 4 over S plus 2. Plugging that in, I'm going to get 4, and then the S plus 2 is going to come down here, plus 4, and then times your R of S, which is going to be the unit step, so that's 1 over S. So that's how I just got my C of S. Solving my C of S and simplifying, what I'm going to get is it's going to be 4 over S plus 6 times 1 over S. Okay, cool. Now what you have to do, of course, is then for a system, you would have to then take the inverse, so partial fraction decomp, and so that would be 4 all over S times S plus 6 is equal to A over S plus B all over S plus 6. Now, what we have to do is we have to solve for A and B. A is equal to S times C of S, evaluate at S is equal to 0. So evaluating that, multiplying by S and 0, that'd be 4/6, which is going to be 2/3. Great job. Now B is going to be equal to S plus 6 times C of S. And evaluating that, S is equal to -6. What we're going to get is we're going to get 4 all over, and then that'd be -6 times negative, and then that one term would cancel out, of course. So it's going to be equal to -2/3. Okay. Now that we got that, what we're going to have to do is yeah. Okay, so we're going to have 2/3 S. So our C of S is going to equal 2/3 times S, and then plus -2/3. So plus -2/3 all over S plus 6. Okay, cool. So what we're going to do here is we can literally just factor that out. So be 2/3 and then multiplied by, and then what's S in terms of our S? It would be, oh, sorry, this is over S. Sorry, I was like, okay, 1/S is just, remember, U of T if you take the and then here if we have, it'd be the minus because we took out the 2/3, and then 1/S plus 6, that's going to be e to the negative, and then here we're going to have our 6t. Okay, and that's ut. Okay, so now what I did is literally just 2/3, and then it's going to be 1 minus e to -6t, and then u of t. Okay, now that we got that, what we're going to do here is, remember, if we have to find our, this is our unit step response. So this is our C of t, because this is written in terms of the time domain. So we have to define the unit step response, which we did here. Now, what if they say, what is tau? Tau is equal to, and so what we're going to have to do here is, you could either look specifically at how your system is made, but there's one important equation for the unit step response that you might have not been exposed to. So C of t is equal to K, 1 minus e to -t divided by tau, and then u of t. What you're going to notice is your K value is the leading term in front, and then your tau value is going to be t divided by, and what you have here. So couldn't I manipulate this to be t divided by 1/6, correct? And so your tau is going to be equal to 1/6. And then you're going to have your settling time is equal to 4 tau, which is going to equal 4/6, which is just 2/3. And then your rise time is going to equal 2.2 tau, which, if you look at this, just doing that, what you're going to get is 2.2 times 1/6 is going to be about 2.2/6. And then you can just plug that in your calculator, and then your tau, your K value, so your final value is going to equal 2/3. Okay, so that's what you get basically from doing that. So what you could do also for your final value, if you want to find a steady state value, remember it's just equal limit as S goes to 0, SC of S. So that is an alternative method of finding your final value in the S domain. Now that we saw that, what we're going to do now is we're going to use this particularly with the Z domain. So now we're going to see it a little differently, but it will still apply the same way, so don't worry. So looking at our equation, what we're going to have is we're going to have the following chart. So it's going to be R of S, and then it's going to go to our summing block. We're taking this as an input, subtracting this one. You're going to go E of S is right here, your error signal, and then you're sampled. And then it's going to be E star of S. And then it's going to be 1 minus E negative T S all over S. And then we're going to have our GP of S. And then we're going to have our output C of S. and then it's going to feed back here. Okay, so what we're going to have to do, say if they give us the GP of S, which is a first order system, which is 4 over S plus 2, and they want us to find C of Z, and then they want us also to find the steady state value here. And so what we're going to have to do from our equation here is to find C of Z. Remember, what we had here is you can form an equation for your output in terms of what you have. And so if you remember for this type of system, because it's a closed loop transfer function, remember for our C of Z, it's just equal to, and then we have G of Z all over, and then if you remember 1 plus HG a Z and then multiplied by RZ, but our H is 1, so it's just going to be G of Z all over 1 plus G of Z RZ. And so what we're going to get for our output here is that our G of Z in terms of what we have here, this is what your G of Z is. So we have to find out what our G of Z is first. And so our G of Z is going to equal our zero order whole, 1 minus E negative T S all over S, multiplied by 4 over S plus 2. That's what we have plugging in. So now finding our G of Z here, sorry, this is G of S right now. We haven't taken the Z domain of it. So when we have to find our G of Z, it's going to be 1 minus Z to negative 1, and then it's going to be Z transformed of 4 all over S times S plus 2. Now, what we have here is we have our G of Z, and we have to evaluate this. So what we're going to notice for G of Z is it's going to be looking at this. Remember, you have to evaluate it at the residues, do the star transform. So we're going to get G star of S real quick is equal to, well, our residues, if I'm just going to plug this in here because we know how to solve this by now, it's literally just lambda, and then it's going to be 4 over lambda times lambda plus 2, and then evaluate it, multiply by 1 minus E to negative T, and then S minus lambda, evaluate at lambda is equal 0, then evaluating at our other residue, which is going to be lambda plus 2, and then it's going to be 4 all over lambda times lambda plus 2, then 1 minus all over 1 minus E to negative T, S minus lambda, and then it's going to be plugging in for lambda is equal to negative 2. Okay, now that we got that, what you're going to notice is lambda cancels lambda, lambda plus 2 cancel lambda plus 2. Plugging in what we have here, lambda is equal to 0, you're going to get 2, and then 1 all over 1 minus E to negative T, S. Okay, for our next one, it's going to be 4 all over negative 2, so that'd be minus 2. And then we're going to get 1 all over 1 minus E to negative T, and then S plus 2. Okay, cool. So now that we got this, what we're going to have to do is, remember, this is our G star of S just for this right here. And so we're going to then have to take the Z transform of it. And so then you can plug in your Z. So that would be your G of Z is going to equal 2 all over 1 minus Z to the negative 1 minus 2 all over 1 minus Z to negative 1 E to negative 2T. Then what we're going to have here is you're going to multiply by Z. So 2Z all over Z minus 1 minus 2Z all over Z minus E to negative 2T is our GZ. Okay. Now that we got that, what we have to do from here is we found the Z transform of this part of the equation. So right now, we only found this. So multiplying by the 1 minus Z to negative 1 here. Sorry, I should probably use a different notation, but that's what he just taught us originally. So 1 minus Z to negative 1, and then we have here 2Z all over Z minus 1, and then minus 2Z all over Z minus E to negative 2T. Then what we have to do here is this part we're going to remember. You can just make this a Z minus 1 all over Z multiplied by 2Z all over Z minus 1 minus 2Z all over Z minus E to negative 2T. Okay, so what we're going to have here is the Z is going to cancel with the Z. and the z here. Okay, so now we're going to be left with multiplying by z minus 1. You're going to notice that this term is just going to become a 2. And then it's going to be a minus 2 and then z minus 1 all over z minus e to negative 2t. So what we're going to get here is you make a common denominator, z minus e to negative 2t all over, and then we're going to get, here this would be a 2 times z minus e to negative 2t, and then minus 2z minus 1, okay? Now, solving this, you're going to get z minus e to negative 2t, and then in the numerator, we're going to get 2z minus 2z, which is 0, minus 2e to negative 2t, and then this would be z, so z minus 2e to negative 2t, okay? Now that we finally got that, what we're going to notice here is that our c of z, what we're going to get in particular is this is going to be, so we got our gz. Now, our cz, remember, is gz all over 1 plus gz times rz. So we just found g of z finally. So to find our c of z, what we're going to do is your c of z is going to be equal to, so here c of z is equal to z minus 2e to negative 2t, and then this would be z minus e negative 2t, and then plus, and then z minus 2e to negative 2t, and then times your rz, which remember is just going to be z all over z minus 1, because that's what we have, because it's just a unit step input. And so now that we got that, what we're going to do is we have to, so sorry, this is a 2. And notice in denominator, we're going to have some terms combine here. And so what we're going to notice is we have z minus e negative 2t and then z minus 2. Okay, so this would be minus 3 and then plus 2. Is this, let me check real quick. Is this minus 2? So this would be plus 2. Yeah, okay, sorry, this is a plus 2 right here, so this is a 2. This is a 2, sorry. I just made a simple mistake there where I accidentally made that up. So this is a 2, then right here, this is a 2. Okay, so now 2 minus 2e to negative 2t, and then what we're going to notice is when we combine this, writing this out, we're going to get a 2 minus 2e to negative 2t, and then in the denominator, we're going to get a z, and then minus 3e to negative 2t, and then plus 2. And then multiplied by z all over z minus 1. And so what we're going to see here is you're going to have your c of z, and then what you were going to want to do is you can take then the inverse z transform if you wanted this one in order to find your c of t. But also what you can do in order to find then the next part of the equation was find the steady state value, find c of z, and then find the steady state value. So we found c of z, but in order to find the steady state value, so this would be correct. To find the steady state value, remember, c of ss is equal to limit as z approaches 1, z minus 1, and then c of z. So plugging that in, we get limit as z goes to 1, z minus 1 multiplied by here. You're going to get, then plugging in z goes to 1, you're going to get 2 minus 2e to negative 2t all over. And then here, you're going to get 1 minus 3e to negative 2t plus 2. Okay, now we're going to see, because I just plugged in 1, sorry for z when I multiplied, and just what we're going to see here is that based on our sampling time, that's going to give us what our output should be. So if our sampling time, that's gonna, let me see, c minus 1, guess that would be a z minus 1. Yeah, that cancel that one, but we'd still have our z here, and then plugging in 1, so that'd just be 1, 2 minus 1 minus 3. Yeah, okay. So based on our sampling time, that's going to determine our steady state output for our equation. So what we should see in order to get this. He said that the sampling time should be near the time constant of the system. And so if you have to determine the time constant of this system, what you're going to notice here is that your time constant, he said, for the open loop, if you remember, it's 0.167 because it's 1/6 when we had our closed loop one, it was just, let's see real quick, for the closed loop system. Give me 1 second. For the closed loop time constant, and then we found 4 over s. Okay, so he was just saying that it shouldn't matter, like it should, but he would give you the p value that you'd have to plug in order to find the final value here. But what he had particularly is he pulled out, so he combined this. So now you can simplify this, right? So you would have I could pull out a 2, so I get 1 minus e to negative 2t all over, and then what you're going to see here is the 1 plus 2 would be 3, and then it's going to be minus 3e to negative 2t. You can pull out a 3 in your denominator, so it'd be 2 over 3, and then 1 minus e to negative 2t in the numerator, and then denominator, you're going to get 1 minus e negative 2t. And then here, recall for your first order system, this is your value of k, right? Which is your final value in front of your first order. So it's going to be 2/3 is going to be your final value. So that would be your steady state value. Does that make sense how you would go there? So what you do basically is you found your actual steady state when you plugged in, but then just factor out in order to get in terms of your first orders, and you're going to notice that, hey, this is my k value in front. Remember, k is the final value that it goes to. And so that was our final value is 2 over 3. So now that we got that, what we're going to look at is specifically our second order systems. And so what we're going to notice is particularly, right here. So, if he does ask, I don't think he's gonna ask this, but if he asks for the settling time, or sorry, the sampling time. So this is your sampling time. Sampling time should be less than or equal to tau divided by 5 for a good response. So based on how much you sample, if he does ask that on the exam, just know that we haven't seen it ever implemented in something, but know that your sampling time should be less than or equal to tau divided by 5 for a good response. So just know this is your sampling time if he does ask in order to make sure. And so what we're going to notice is we're going to move on to second orders, and they're very similar. So for second order systems, we're going to have the following, where it's defined in terms of our g of s is equal to omega n squared all over, and then it's going to be s squared plus 2 zeta omega n s plus omega n squared, okay? And so what we're going to see here is that where are poles of our systems? Remember, it's equal to negative zeta omega n plus minus j omega n square root of 1 minus zeta squared. Because remember, when you take the quadratic of the denominator, this is what you're going to get. And so that's what we're going to see here. So when you graph it on the s-plane, remember, you're going to have your two poles. And say if they're like right here, we're going to have specifically, this is known as the omega n, the distance to the pole. This is known as your angle right here. And the distance that goes out is known as negative zeta omega n, which is equal to negative sigma d. And then up here, this is your omega d, which is equal to, your j omega d, which is j omega n square root of 1 minus zeta squared. Okay, so now that we have that here, so your j omega d is equal to j omega n square root 1 minus zeta squared, then here negative zeta omega n. So what we're going to have is basically, for second orders, you got to remember they have a few things. So the settling time is defined as 4 divided by zeta omega n. The peak time is defined as pi divided by omega d. And then we're going to have our percentage overshoot is defined as 100 e to the negative pi zeta. So negative pi zeta, all divided by, and then it's going to be square root of 1 minus zeta squared. Okay, so those are the three main things. So this is your second order system, what it's normally defined as. And then you have these three parameters associated with it. And so if you have to find zeta, your zeta is equal to negative natural log percentage overshoot all over 100, and then divided by, and then it's going to be pi squared plus, and then natural log squared, and then it's going to be percentage overshoot over 100. Okay, so that would be another formula in order to find zeta if you're given the percentage overshoot. Or you can use a table he provides. So let's look at specifically what we need to do for an example, just with a basic second order system. We're pretty used to these. So if our GVS, say if we're given the following block diagram where we have an RVS and it goes through to a summing block here, we have a positive and we have a negative. And then we have our EVS, and then it goes through our GVS here. So this is our EVS, and it goes through our GVS. And then we get to our output CVS. So what we have to do is our G of S is equal to 1 over S times S plus 1. And so we're going to have to find the unit step response. So we're going to have to get here C of S. And then they're asking for the transient specifications. So that would be your settling time, your rise time, your peak time. There's not rise time in second order systems. Your percentage overshoot. Then they're going to want to know the final value. So the steady state. So what we're going to have to do here is trying to solve for this. What we're going to get is specifically, if we have to solve for C of S, remember for a second order system, well, for any type of system with a closed loop, C of S is going to equal our transfer function, which is G of S, all over 1 plus G of S, okay? So now what we have to do is, looking at this, we're going to have to solve because we know what we have here. So this is just going to be 1 all over S times S plus 1, and then plus 1, okay? And then that's 1 all over, and then here we're going to get S squared plus S plus 1, okay? Now we need to find the settling time. So our settling time is going to be 4 divided by zeta omega n. So remember, this term right here is 2 zeta omega n right in front of this. So right in front is 2 zeta omega n. So 1 is equal to 2 divided by zeta omega n. So technically zeta omega n is equal to 0.5. And so this is going to be 4 divided by 0.5 is just going to equal 8 here. And now that we got that, we need to find the peak time. So the peak time is going to equal right here. This is going to be, remember it's defined as pi divided by omega d, which is going to be pi divided by, and then our omega d. Remember your omega d from the second order system is defined as omega n square root of 1 minus zeta squared. Square root 1 minus zeta squared. Okay, so we need to solve for omega n and zeta squared. Remember, this term right here is your omega n squared. So omega n is just equal to 1. We know that. And then what about our zeta? Our zeta, remember, we found zeta omega n is equal to 0.5. Knowing omega n is equal to 1, we can deduce that zeta is equal to 0.5. Plugging that in here, you're going to get pi all over 1 square root of 1 minus 0.5 squared, which is going to equal pi divided by 1 minus 0.25, that'd be 0.75. Plugging that into my calculator, I'm going to get about 3.628. Okay, now that I got that, I need to find my percentage overshoot. My percentage overshoot, remember, is equal to 100 e to negative zeta pi 100 e negative pi, and then it's going to be zeta divided by square root of 1 minus zeta squared. Which, if you plug in, we found pi for ours. Sorry, not pi. We found zeta. And so then if you plug that in, you get 16.3%. Okay, so we found all of our specifications. Now we need to find a steady state value. Remember, your steady state value is going to equal because this is just dealing with the S domain, it's the limit as S goes to 0, then C of S, right? And so we found our C of S. So you just plug in 0, it's going to be 1 over 1, which is just 1. There you go. So that's pretty much how you would do that for your final value. And now we're going to look at the discrete domain and try and solve it. So down here, we're going to have our R of S, so very similar, and we're going to have our summing block here. So it's going to combine our two. So this is our E of S here, and of course this is your E star of S. And then we're going to go and we're going to have 1 minus E negative TS all over S. And what we're going to have after here is GP of S. So your plant transfer function, and then your output is going to be C of S. Then it's going to come back and feed back into our system. So it says find the unit step response. So find C of S for the unit step response. Then it's going to say, and then the final value. So steady state value. So what we have to do here is we're going to have to find C of S first, and then we're going to have to find the final value from, sorry, if it says find the unit step response, sorry, and this is in the Z domain, it's C of Z. I don't know why I said C of S, because that would be for the S domain, but now we're working with the discrete domain, so it'd be C of Z. And then what we're going to have here is basically what we need to do is we need to find the closed loop transfer function here, because remember your C of S, if you do write the equation, it's going to be your G of S multiplied by your E star of S. And so remember, C of S is equal to, and then it's going to be G of S times E star of S. And then we know our E of S is defined as, because it's the input to the switch, it's R of S minus C of S. Okay, and so then here, what we can do from here is we need to find our closed loop transfer function. So if we plug in what we know here, we're going to get our E of S is equal to R of S, and then minus, and then we're going to have G of S times E star of S. Taking the star transform of both sides, what you're going to get is star transform here, star transform here. And so E star of S is equal to R star of S, and then minus G star of S, E star of S. And so then we're going to then move this over to the other side, and solving for E star of S, you're going to get it as R star of S all over 1 plus G star of S. Okay, now what's going to happen is plugging now in your E star of S, what you have here is you're going to have your C of S is equal to G of S times your R star of S all over 1 plus G star of S. Now remember, what we have here is taking the star transform of both sides, you're going to get C star of S is equal to G star of S times R star of S all over 1 plus G star of S. So that's just going to be C of Z is equal to G of Z times R of Z, and then all over 1 plus G of Z. So you derive the transfer function there. And so now finding your G of Z, what you're going to get specifically is, remember, this is your G of S right here. So now you just have to do that derivation where your G of Z, because that's a 0 order hold, so it's just going to be 1 minus Z to -1, and then the Z transform of, then your plant transfer function for this system is going to be the same one as up above. So here, your GP of S is going to equal, so you guys know it's 1 over S times S plus 1. So that's what your GP of S is. So here, taking the Z transform of that, you're going to get 1 all over. And then remember, it's going to be an S squared times S plus 1 because from your zero order hold, you have a 1 over S contribution. So now when you do that, what you're specifically going to get here is that we have to do the residue method on this one. And so you would apply the residue method, and then you plug in your G of Z. Once you get the final result into here, you're going to get your C of Z, and then you solve for your C of Z, you'll get your unit step response, and then you'll get your final value, which remember, your final value in terms of the Z domain, it would just be the limit as Z goes to 1, Z minus 1, C of Z. That's how you would solve for your final value. So if that's how you'd solve the problem, you know how to find G of Z, and then you just plug it in and you can do it. I'm not too worried about that one. Now that we talked about that one, what we're going to do is we're going to specifically look at the sampling rate here for second order systems. So he defined the sampling rate as less than or equal to. So if he asked for second order systems, the sampling rate should be less than or equal to omega n divided by, omega n divided by 5, I believe, is what he went up with. 2 pi times tau omega n divided by 5. That's what he had in his notes. He changed it. Yeah, so it's omega n divided by 5. So now that we have this, what we're going to see is that if we have an F, so this is for second order systems for your sampling rate. Second order system, so make sure you just have that written down so you're good. What you're going to see here is if we have a pole, so if our F of S is equal to 1 over S plus A, you're going to notice that transfers in the Z domain. Remember, in your F of Z, it's going to equal Z all over Z minus E to the negative AT. And so here, what you're going to notice is if you solve for Z, you're particularly going to get, for your pole, it's going to equal E to the AT, correct? E to negative AT. So what you're going to have is, remember from first order systems, your S is equal to negative A. And so what this is going to be is it's going to be E to the S1T. Say if you plug in for yours, that's what you're going to notice. Because we're going to have our specific ones where, remember when we had 1 over S plus A, S is equal to negative A from here? You can deduce that. So plugging in for negative A, your S, that's how you get this format right here. And so now, what we're going to see specifically is from here, you can separate it. So your Z, this would be like if you have Z1 is equal to E to the S1T, we're going to see you can split that up in terms of E to the sigma 1 plus J omega 1T, okay? And so what we're going to do is this can be split into both a magnitude and a phase. So it's going to be equal magnitude of Z1 and the phase of Z1. So what we're going to have here is your magnitude of Z1 is going to equal to E to the sigma 1T, and then your phase of Z1 is going to equal omega 1T. Okay, because that makes sense. Your phase, and then this is going to be right here with your J term and your magnitude. And so what we're going to have now is we saw that how you could get the magnitude and the phase just by applying your Z transform, which remember, Z is equal to E to the ST. So here we just applied a Z transform. We saw a pole at negative A corresponds to a pole in the Z domain at E to the AT. And so that's what we had here, plugging in S for negative A. You can write it in this format where we're going to see that you can get the magnitude and phase. And so this is going to be helpful because in terms of our system, let's say we have a first order system, which is given by the following transfer function, and we have to find the time constant of it. It's the same as Z domain, for an example. we have the first order system, T of Z is equal to 0.3625 all over, and then it's going to be Z minus 0.4562. And the sampling time, T, is going to equal 0.1. So they want to know, solve for tau. Okay, so right off the bat, there's only one pole, right? So this is a first order system. And so what we're going to see is solving specifically, our pole is going to be at E to the ST, right? And so here that's equal technically to 0.4562 where our pole's occurring. Now taking the natural log of both sides, we're going to get ST is equal to the natural log of 0.4562. Plugging that into your calculator, in solving specifically just in terms of S, you're going to get natural log of 0.4562 divided by your capital T, which is 0.1. You're going to get S is equal to negative 7.842. Remember, for the first order systems, when we had, just a loose side note, wasn't S equal to negative A where the pole occurred? So here, this is negative A, so we can reduce that A is equal to 7.842. And remember how our first order systems, they were always written in this format. Sorry, for first order systems where the tau is equal to 1 over A. Here, taking 1 over A, we're going to see that tau 1 over A is going to equal 1 over 7.842, which is going to equal 0.1275 seconds. So that's how you would find your tau for your first order system from the transfer function. So supplied the transfer function, we know the pole occurs at Z equals E to the ST. Solving for S, remembering that S is equal to negative A, and we find A, 1 over A gives us tau. That's for a first order system. Okay, so now that we found the first order system, we're going to have to look at a second order system in particular. So second order systems are a little more different than the first order systems. So if you remember, for our studies, when we have a second order system, particularly one with like conjugate poles, a lot of times it might be given in the following format, where we have our T of Z, so this would be second order. T of Z is equal to, and then say if we have 0.3679 times Z plus 0.7181, then we have repeated poles, they're conjugate poles, sorry, Z minus 0.5 plus J 0.6181, and then Z minus 0.5 minus J 0.6181. Okay, so what we have to do here is, knowing our system, it's going to be given in the following format where we're going to have to solve. Notice that we have conjugate poles. And so what we have is, recall Z1 is equal to E to the S1T, where this is equal to E to the sigma 1 plus J omega 1T. Okay, so sigma, what if you solve just for sigma 1, you're going to get it's equal to natural log of Z1 divided by T. If you solve for omega 1, you're going to get the natural log, sorry, the phase of Z1 all over T. That's the phase component. And so what we're going to get is, specifically when you solve for this, notice that your poles, Z1 is equal to 0.5, and then plus J 0.6181. If you take the magnitude, so remember, when you take the magnitude, you're going to get, you take the square root, and then you take 0.5 squared plus, and then 0.6181 squared. You're going to get the following in the phasor format. We're going to convert from Cartesian to phasor. We're going to get 0.795. Phase is 0.890. And so our sampling time, say if our sampling time is defined as 1 second. So what we have to do is, finding the sigma 1, we get sigma 1 is equal to, Well, this is the magnitude, right? So it's calling for 0.75995, and it's going to want the natural log of this, and then divided by, and then what's our sampling time? 1 second. What about omega 1? It's equal to the phase, which is 0.890 divided by, and then it's 1 second is our sampling time. So solving for this, what we're going to get specifically is our sigma 1 is going to equal negative 0.2294. Our omega 1 is equal to 0.890 radians. Be careful when you solve for this. You need to make sure it's in terms of radians and not degrees. So on your calculator, make sure you're not in degree mode or else everything's going to be wrong. So make sure you get this in terms of radians. And so what we're going to have to do is remember for a second order system. Sorry, give me a sec. So remember for a second order system, what we have is our omega n is equal to square root of sigma 1 squared plus omega 1 squared. Okay. So I'm throwing a lot of equations. Remember for a second order system, sigma 1 and omega 1. You have to represent your poles, the complex poles, in terms of the magnitude and the phase part. So you have to represent them in order to plug it in here. And then your omega n is equal to the following formula, and your sigma is equal to sigma 1 all over omega n. So these are what you need to know for the second order systems in order to determine their response characteristics. And so from here, if we have to solve for our omega n, you take the square root of this squared plus this squared, you're going to get the following. You're going to get 0.919 radians per second. And then here, for your sigma 1 divided by omega n, you're going to get this divided by, and then your omega n you just found. So it's going to be negative 0.2294 divided by, and then 0.919. You're going to get, when you plug that in, 0.25 about. And so now that we got that, notice though here we got a negative for this. So I think he defined it in terms of, because this is correct technically, like because it is negative. So I feel like this, make sure your stamping ratio can't be a negative number. So you should just know that it should be positive. Because remember, it's always like between 0 and 1 usually for a second order system. So you should know that this is just a positive by heart. So it wouldn't make sense if it's negative. And then what we have to do is we have to solve for the percentage overshoot in the settling time here. So now that we found those terms in terms of the S-plane, your overshoot is equal to 100 e to negative pi zeta divided by square root of 1 minus zeta squared. So using those equations, you found what your zeta and your omega n is. So plugging in your 0.25, what you're going to have, yeah, I think it's just absolute value, Fernando, too. It just should make sense logically that your damping ratio isn't a negative number. So it might be I'm thinking there might be an absolute value there. He just didn't include it in his definition, but you should know this should be a damping ratio. It should be positive. And then what we're going to see here is the percentage overshoot is equal to plugging in your values. You're going to get 44.3%. And remember, your settling time is equal to 4 divided by zeta omega n. Plugging in your values, you're going to get 17.43. A big thing in the textbook, they asked us in the homework, find the tau value. Remember how for a second order system, or if we approximated settling time as 4 times tau, so your tau would be just your settling time divided by 4. And so that's why we can say it 1 divided by a zeta omega n. So if they do ask that, you could solve for your tau value if it wasn't asked. So for the second order systems, if you had 2 conjugate poles, you literally just need to find the representation in terms of the polar, so the magnitude of one of the poles and the phase. And then what you do from that, make sure your phase is in radians. You find your sigma 1, your omega 1. You can find your natural then frequency and then your damping ratio. And then using that, those 2 pieces of information, you can solve for your time domain characteristics. And so that's pretty much what you have to do in terms of there. And then there's going to be the air. I'm going to take a quick break real quick for 3 minutes. So we'll pause and then we'll come back. Okay, so now we're going to get started with steady state air. So we saw sort of like the time domain characteristics of first and second order systems. So steady state air is very similar in the Z domain, like to the S domain. So what we're gonna notice is there's a nice little like table. So basically, remember how we said like there had to like be a peer integrator in your system, like based on how many your system type is determined by like how many peer integrators you have. So when we're talking about steady state air, the system type is defined as, instead in the Z domain, it's going to be the number of Z minus 1 terms in the denominator of your open loop transfer function. And so that's what we're going to see here. And so you can still use the table. So a lot of times when we have our steady state air, we define it particularly as for the step input. So for a step, then we have one defined for a ramp, and then we have one defined for a parabola. And so what we're going to see is for type 0, type 1, and for type 2. So if you have no Z minus 1 terms in your denominator of your open loop transfer function, your error is going to be given by, for a step input, 1 over 1 plus Kp, where Kp is your position error constant. Your error is going to be infinite for a ramp and infinite for a parabola. But for a type 1 system, you're going to have 0 steady state error. You're going to have 1 over kV. And then here you're going to have infinite error per parabola. And for a type 2 system, you're going to have 0, 0, and then you're going to have here 1 over Ka. So you probably want to know how those are defined for our types of systems and how steady state error is defined. So this is just like the chart if you have a unity feedback system. This is perfect, and it only applies for unity feedback. So that means your H of S term would be 1. So for unity feedback. Okay, so in general, what is steady state error defined as? So steady state error is defined as the limit as k goes to infinity of your E of kt, which is also the limit as z goes to 1, and then z minus 1, and then E is Z. And so what we're going to see here is sorry, your steady state error is defined as the limit as Z goes to 1, Z minus 1 E is Z in the Z domain. Okay, so let's look at an example here. How are your position error and your velocity error defined in the steady for the Z domain? So we're going to see that the Kp is equal to the limit as Z goes to 1, G of Z. And so this is your G of Z, remember, is like your forward transfer function. And then your Kv is going to equal your limit as Z goes to 1, and then it's going to be 1 over T, Z minus 1, and then G of Z. Okay. So these are just like a bit of definitions I sort of threw at you for the steady state error. And you're probably wondering like, hey, how did we get these? And so remember how when we were dealing with the S domain, you sort of had the Kp and you had the Kv. And here for the Kp, it was just the limit as S goes to 0, and then it was G of S. And then here we had the limit as S goes to 0, and then it was S G of S. It's very similar here. So instead of, it's just G of Z instead of G of S. And then here we have, instead of S, we have Z minus 1. And then due to sampling time, it's 1 over T. So sampling time just affects how much air we have as well. Because if you have more samples, then you have less air. If you have less samples, you're going to have more air in your system. And so what we're going to see here is, let's do an example where we have to find the steady state air. And so then we can sort of put everything together. And so for an example, it's going to be R of S, and it's going to go to a summing block here. And so the summing block is going to have our sampler. So remember, this is just our error signal, and then we have our sampler here. And then we're going to have our 1 minus e to negative ts all over s. So this is the zero order hold. And then we have our gp of s, which is our plant transfer function here. So the plant transfer function gp of s, what we're going to notice is that they're going to define it for us. And then we have our output c of s. And so this right here is a unity feedback system. And so our GP of S is defined for a system as K all over S times S plus 1. And so what we're going to see is we need to find the steady state error for a unit step. So find the steady state error for if our input is a unit step, if it's just like U of T, how are we going to do that? And so remember, this is a unity feedback system right here, so I can apply my table. So let's look at our forward transfer function. And remember, this is your G of S right here for this example. This would be your G of S, your forward transfer function. There's no other blocks there's like no controller here. So if there was a controller, you do G of S times whatever your controller, because that would be in the forward path. But here we just have these. So our G of S for our definition here is G of S would be equal to, and so what we're going to see is it's going to be 1 minus e to negative ts all over s times, and then this would be k all over s times s plus 1, okay? And so what we have to do is finding our G of z. What this is going to be is, remember, it's 1 minus e to negative 1, then it's going to be z transform of, and then here we're going to have k all over s squared times s plus 1, okay? So now that we got that, what we need to do is, this is going to be our G of z is going to equal, and then here we're going to see when you have to take the z transform of this term here, what are you going to get? And so looking at what we have here, notice that there is a z transform table here, s squared all over s plus, and then if this is 1, say if we just have 1 here, it's going to give us the following equation for our z transform here. And so just popping that in, what we get is, this is just 1 for a, so it's t minus 1 plus e to the negative t, and then we're just going to substitute in 1 for the rest. So you know where I'm getting that from. So here I can rewrite this as z minus 1 all over z, but now the z transform of this is going to be, because our k is a constant, so it can just come out in front, so it'd just be 1 over s squared times s plus 1. And so what we're going to get here is, this would just be a t minus 1 plus e to negative t times z plus, and then 1 minus e to negative t minus t e to negative t, and then we're going to have all over, and then down here we're going to have a z minus 1 times a z minus e to negative t, okay? And so now seeing that, what we're going to get specifically, I think they implied that we applied. Let me check real quick. Multiplying by z canceled out that one, I think. Let me check real quick. Z minus 1. Oh, okay. Yes, because this would have a z and then a, yeah, okay, then I would need to add a z. So when they applied this, they already applied this to it. And so this would be what you do if you took the z transform and then you multiplied by, you would get the following. And so now what we have to do is look how many pure integrators of z minus 1, that refers to how many system type, what our system type is. We have 1 z minus 1, so our system type is 1. So system type equals 1, because we have 1 z minus 1 in our denominator of our open loop transfer function. So since our system type is 1, our steady state error, it's a step, right? So the steady state error is 0. So the error to the step input is going to be equal to 0. What if we have a ramp input? Then it would be 1 over kV, right? And so for a ramp input, the steady state error is going to be defined as 1 over kV, and kV is defined as the limit as z goes to 1, and then it's going to be 1 over t z minus 1, and then it's going to be g of z, which if we look here, if you multiply this entire thing here by z minus 1, this will cancel with this. And then plugging in 1 here, you're going to get, what we're going to see is you're going to have, for r's, it would be, for all your z's, so this would be 1 times this. And so we would notice that, then our sampling time also, dividing by our sampling time, in ours, the sampling time would be 1 over, because this would, if you plug it all in and you do all the math, what you're going to get is your steady state error is going to be 1 over k. So you know, when you plug this in, this should give you k here, and then you're going to get 1 over k. So just plugging all that in, you can find the error to the step input because it's just type 1 here, and then the error to the ramp input would be 1 over kv. And then solving for your kv here, if you literally just multiply by z minus 1, you're going to notice that this cancels in the denominator here, and then you're going to have 1 over t, and then when you plug it in specifically, you're going to get k. And so 1 over k, because your steady state error is defined as 1 over kv, and if kv is equal to k, that's how we're able to solve for this. So that would be how you get the error for yours. And so what we're going to notice is that that's pretty much how you're going to define for your steady state error. Everything is pretty similar to what we've done before. And so now that we've done that, we're going to look at the stability. So this one is where we probably won't put a lot of time in because I feel like it's going to be a lot on this. So stability analysis. If we have an output, so our output, let's define it as y of kt, it's going to have a forced response and a natural response. So the forced response refers to, you know, like the external input. So if you input a step, if you input a ramp, where the natural response is going to be like due to the initial conditions. So normally you write it as yz is equal to, and then because this is due to like your forced input, it's rz, what you're forcing into the system. And then your natural response is due to the initial conditions all over your dz, which is the characteristic polynomial of your equation. So when you're talking about internal stability, you're looking at the natural response. So this is your internal stability. You're only looking at the natural response. But when you're looking at your external stability, that's when you're looking at the external input, so your RZ. So that makes sense, right? You know, you're looking at what's externally coming into the system. So if you're applying a step or a ramp. So that's sort of considered like our force response. So what we're going to do is a system is externally stable if every bounded input results in a bounded output. And so what we're going to see is we're going to have basically when we're talking about like stable or not stable, if we look at a system such as G of S, let's look at this one system. G of S is equal to S minus 1 all over S minus 1 times S plus 2. Okay. Is this internally stable or externally stable? So what we have to look at is we notice that we have two poles here. We have a pole at +1 and a pole at -2. And so then what we're going to see within our design, though, is these two cancel with each other. So it's a pole zero cancellation because it's right on top. Realistically, this doesn't happen. So theoretically, these should go away with each other. And so then we would say that, oh, there's a pole at S equals -2, so it's externally stable. And then what you're going to notice, though, is really internally, when we look at this, from our standpoint, is it's not internally stable because we have two poles. One at S1 is equal to 1, and one at S2 is equal to -2. So technically, this is not internally stable. Because what you're going to notice within our system is that we have our two poles, and realistically, this doesn't apply where we have the pole zero cancellation. He just said theoretically, and then you would just get a pole at -2, so it's externally stable, but realistically, you're not going to have this type of system. So what we're going to do here is, if we're just looking at our system in the standpoint of, if you close the loop on it, so if you made the closed loop system, which would be your T of S, right? Your T of S is equal to G of S all over 1 plus G of S, if you just have unity feedback. And then that would be, within your system, you would have S minus 1 in the numerator all over, and then you'd have, down here, it would be your S minus 1 times S plus 2, and then plus an S minus 1. And then what you get is you get an S minus 1 all over. And then here you're going to have, let me see if this, oh, sorry, because if you had the cancellation, it would actually just be 1 over S plus 2. So you get 1 all over, and then this would be S plus 2 plus 1. So you get 1 over S plus 3. So you notice that you'd only have one pole at -3, so then it would be stable. This is just like a definition. He had like a example, but don't worry if you don't understand it because you're not tested on it. So don't worry about that one. So we're going to look at how we define basically our systems later on for stability. There's different methods you can use. And so what we like to say is that a lot of times when we're looking at stability, we like to have the unit circle. And so what you're going to notice is, I think this picture does a better job than just explaining it. If you have your poles, when we're now in the discrete domain, so it's going to be stable if all the poles are within the unit circle. It's a stable system. Notice for the poles in the unit circle here, it decays and goes to 0. It's decaying and going to 0. Notice though the poles outside the unit circle, it's increasing over time. It's increasing over time. And so that's not stable. So it's unstable because the poles outside the unit circle. It's marginally stable if you have poles on the unit circle that are not repeated. So if you just have like single poles and then the others are inside the unit circle. And so I think that picture does a good job at least explaining stability for us in the discrete domain is defined as within the unit circle, or if you have poles on the unit circle that aren't repeated. So now we're going to look sort of at our types of stability tests. And so he talks about this one thing, which is called like the W plane we have to learn. And so we started out with our pod A approximation. If you guys remember like pod A approximation, how it's defined is, it's basically, if we have e to the st, it's written as e to the st all over 2 divided by e to negative st all over 2. And so he splits it into a numerator and denominator, just two things. And you can define this as 1 over 1/2 st plus ... And then 1 minus 1/2 st and then plus ... It can keep on going on and on forever. And so we approximate it because remember, z is equal to e to the st. So z is approximately, we just look at the first two terms. So 1 plus 1/2 st all over 1 minus 1/2 st. Okay. And so if you solve for s, you're going to get s is approximately 2z all over t, 2 over t, and then it's going to be z minus 1 all over z plus 1. Okay. And so we like to look at the W plane, which is defined exactly. He says that we show the W plane as the exact. So it's exactly equal to 2 over t z minus 1 all over z plus 1. So the W plane is close to that plane, but it's called an exact mapping. And then from this, you can say that z is equal to 1 over 1 plus z, and then wt all over, and then 1 minus 1/2 wt. Okay? And so this is called the bilateral transformation. So if you see this, it's called the bilateral. So I think there's a good image on this one where we're So this is a bilateral transformation right here. As these two equations, what we see going from one form to the W plane and going back to the Z plane from the W plane. So I think this does a good job where you see all three types here. You're going to see the unit circle, which is our Z plane right here. And the Z plane is defined basically as anywhere inside our unit circle is stable. So in the W plane, it's anywhere on the left-hand plane. And you can see like the transformation, the bilateral transformation, converting between one and the other. Where the S-plane is defined, you know how we only had like the primary strip and then we had like the repeating strips? That's our S-plane, and it's defined by Z is equal to the ST. And then if you take the natural log of both sides, solve for S, you get this one. So it's just converting between different formats. There are bilateral transforms used for this W plane. The W plane maps the entire left-hand plane, where the S-plane is only your primary strip. And so that's what we have there. And so we're going to look at basically now an example where we actually get to apply stability tests, because this will be important for sure. So we need to know how a system is stable. So let's do an example now after all that conceptual stuff. So we have R of S here. And so that's our input coming into our system. So we have a summing block coming in, and then we have their negative in here from our feedback. So our error signal is defined here, and we have our sampling. And so this is our E star of S, of course. And then we're going to run into our transfer function here, our zero order hold, which is 1 minus e to negative ts all over s. And then we're going to have our plant transfer function, gp of s. Okay. And what's going to happen after is we're going to have our C of S at the output, and then it's going to go here, and we're going to have our feedback system. So if we're given that GP of S is equal to K all over S times S plus 1 for T is equal to 0.1, what values of K make the system stable? Okay, make the system stable. So what we're going to see here is that we first need to find the closed loop transfer function, right? And from the closed loop transfer function, we're going to look at our characteristic equation of our polynomial, and then we're going to then map it to the W plane. And then from the W plane, we're going to then see how we can solve for it. So first, we need to find the closed loop transfer function, as you should, because you're always looking for like your characteristic equation, which is the denominator of your closed loop transfer function. So first we need to find G of Z, and then it's a unique feedback system. So it's just one G of Z all over 1 plus GZ. So here we have our G of Z, or G of S right now. So to find G of Z, it's going to equal 1 minus Z to negative 1. And then it's going to be Z transform of, and then it's going to be GP of S all over S. Okay. So our GP of S is defined here. And so we're going to get now if we try doing the Z transform of that one, it's going to be K all over S squared times S plus 1. And then times 1 minus Z to negative 1. Okay. And so what we're going to do here is when we find this, you're going to get the value of K T minus 1 using the Z transform table, e to negative TZ plus 1 minus E to negative T minus T e to negative T, and then Z minus 1 multiplied by Z to the negative ET. And so what we're going to see here is when we go and solve for it, we need to find the closed loop transfer function. So the closed loop transfer function for Z is going to equal our GZ all over 1 plus GZ. And so here, what we're going to have to do is our GZ is the numerator, and then you can bring this down into the denominator. You're going to get the following equation, which is K times T minus 1 plus E to negative T, Z plus K 1 minus E to negative T minus T E to negative T. So the numerator really isn't going to be important. It's more about our denominator of our closed loop, because that's our characteristic equation. So we're going to get K times T minus 1 plus E to negative T minus, and then 1 minus e to negative t, and then z, and then plus k, 1 minus e to negative t, minus t e to negative t, and then we're going to have plus e to negative t. Okay, so here, what you're going to notice is for t, we can now plug in is equal to 0.1. Our characteristic polynomial is going to equal z squared plus 0.0048k minus 1.9048z, sorry, times z, and then plus 0.0048k, and then plus 0.9048. Okay, now with this, remember, we're going to map to the W plane. So I'm going to now get it in terms of dW. So remember, it's just d is z, and what we substitute in for W, we just talked about W. If we need to solve it in terms of W, we can plug in now. We have it in terms of Z, so just putting in terms of W, substitute for Z, this right here. So we're going to get Z is equal to 1 plus 1/2 WT all over 1 minus 1/2 WT. Okay. So we're going to substitute that into our equation. And what we're going to get is what you can do to help simplify it is we already know that our t is 0.1. So you can just, this is 1 plus 0.05W all over 1 minus 0.05W. So what you're going to get for your dW after substituting is it's going to be 2381W squared plus 2380 minus 120W, and then plus 2400K. And then what we're going to have here is, minus 120K all over, and then here in our denominator, we're going to get 625 omega squared minus 2000, 25,000 plus 250,000. Okay, so now what we're going to do is we got it in terms of dW from our characteristic polynomial. So we can now use the Roth-Hertz table. You guys remember what that was? So we did all of this. We started from the basic. We found the closed loop transfer function. We found the characteristic polynomial here. And you have to write the characteristic polynomial, d is z, in terms of dW. So you substitute in for z, the following. You get the denominator now. From this denominator, we're going to make our Roth-Hertz table. So your Roth-Hertz table, instead of having s's, it's going to be omega squared, omega to the power 1, omega to the 0. And then substituting in your coefficients here. Sorry, you don't look at the denominator. I'm bad. You look here. Look here at your numerator. Weird, it's W. So W, literally W, you do the inverse of what you're used to. So 2381. So make sure, make note, you look at the numerator, 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 numerator on your dW term. Just look at the numerator, not the denominator. So here we got our W squared term. Now, what we have to do is that's weird. Did he? Give me a sec real quick. Did he do that right? Let me check my homework real quick. I'm just a little skeptical because he put the same power right here. I feel like this term should have been here. Fernando or one of you guys, I feel like shouldn't that term be here because it's W to the power 1? Let me check.
It looks like it yeah, so the 2381 should be in the S squared, and then the 2380 minus 120K should be in that part, and then the last one should be 2400K. I
Shouldn't
think it
this
might
one
be,
be swapped with this one?
yeah, because it'll be S squared and then it'll go evenly.
That's what I thought too. Let me check my homework one just to make sure. Give me like 1 minute, guys, because I know my homework one's correct. To make sure it. I think he just made a mistake in the notes, but let me check. Okay, so here W. Okay, yeah, in my homework one, I defined it. Oh, I only had an omega to power. What they define is they have the W. Yeah, this should be in terms of W, and then yeah, it's W squared, then W0. So I think he made a mistake here, and then this is W to the 1. So these two should have been flip-flopped here. If that should have been correct then. So I don't think you do use the numerator, but in the homework examples, which I looked in the book and I made sure the answers made sense. You'll see here that they got it in terms of DW as well. So here this was their DW, and then here's my numerator, and so I just got all of my like terms. So this is just my W power 1, my W power 0, W power 1, and then W power 0 down here. And so you would go, if you had a W squared term, then it'd be W squared, then W0. So you'd follow the same thing as the Rothberts. I just think he made an error in his lecture notes. And so this should be 2381. Here it should be 2380 minus 120K. And then here it should be 2400K. Okay. Now that we have that, what you're going to notice down here is what's going to copy down is basically your 2400 is going to come downwards. So here we're going to notice that this would be our 2400K. If you remember from the Rothberts criterion, if you're trying to solve for this one, you would do it's going to be for your Rothberts, it's negative, and then it's going to be this column here. So if you're trying to solve for this position, it would be to get this position right here, you do -1 over, and then what's your bottom left corner one? It's going to be your 2380 minus 120K. And then you're going to notice here this, if you try taking the determinant then, a 2381 2400K. And then if you have 2380 minus 120K and then 0 here, there's nothing that you're gonna get -2400K times this divided by this. This will cancel this, and then you'll just get -400K will cancel with the negative here. And so then that's how you get this. It's just -1 over, and then your bottom left one times the determinant. And so what we're going to notice for a range of K now is you got to get 2380 minus 120K is greater than 0, and then 2400K is greater than 0. And so what we're going to notice here is K must be greater than 0. And then here, if you solve for K, you're going to get 2380 must be greater than 120K. Then you're going to get K must be then less than, and then we're going to get 2380 divided by 120. When we solve this, particularly 2380 divided by 120, we're going to get 19.83, which is funny because that matches up with his solution. So I think he made a mistake in his answers, because this would be less than 0. 20 is less than 0, 120K is 2380. Yeah, no, he made a mistake because ours makes sense. We have the same range, but his would give you the opposite range. So he made a mistake in his notes. So just be aware of that. You start from the omega squared. So this is your omega squared term, then your omega 0 term. And then this is the omega power 1. And then you do the -1 over the bottom left position, and then times the determinant of this, you'll get then your term right here for omega to the power 0. Then you find your range of K for stability. So this is using the Rothberts criteria. So from the start, what we did is we found the closed loop transfer function. We got the characteristic polynomial from the denominator. We put that in terms of W, and then use the numerator. Use the numerator, the W term, plug that into your Roth-Hertz table and get your range of K for stability.
It's a question. So you can only do this when you convert that to W?
You can only do the Roth-Hertz when, yes, you convert to W.
Gotcha.
You
All right,
can't do
thanks.
this like with Z's in it. Does that make sense?
Yeah, yeah, it makes sense.
So if you have to find stability, you have to convert from the DZ, your characteristic polynomial, to the W. Because remember how the Roth-Hertz applies to all poles in the left-hand plane? When you're in the Z domain, you're in the unit circle.
Oh, okay, yeah, that makes sense. And then in the W plane, it's like the semicircle, but on the left side.
W plane is like all the left-hand plane.
Yeah, yeah, it's
Yeah.
like it's half of the circle, but on the left side. Man, thank you.
It's like a circle with infinite radius. Like because it takes up the whole left-hand plane, the W plane. Does that
Oh
make
yeah,
sense? It takes
that's
up
right.
like the whole left-hand plane. So it's just like the S plane. Remember how like going back here, Fernando,
Yeah.
the W plane, let me show okay. So what we see here is this is our Z plane, which is only the unit circle. Okay. The
Right.
S plane, remember when we had star of S, it's the star of S, it's only the primary strip, right?
Right.
And so this is primary strip, it's nothing outside. Where the W plane is everything in the left, it looks like a circle, but it's a radius as it goes to infinity because it covers the whole left-hand plane.
Oh, I see. I didn't even see that part. Okay, that makes sense.
Mhm. And remember, the Roth-Hertz is used to determine any of the to make sure it's in the left-hand plane for stability, the entire left-hand plane. So that's why we have to convert to W plane to apply the Roth-Hertz test.
That makes sense.
Okay. Now that we have that, we're gonna look at our next one, which our next stability test is the jury stability test. Um, the jury stability test is a little more difficult, not gonna lie. But well, I think it's simpler in terms of less calculations, but it's just new, so it seems more difficult. But you have to find the characteristic polynomial. And so for the jury's test, we'll walk through it and see our example. You're gonna have the characteristic polynomial d of z is equal to a to the n z of n plus a to the n minus 1, z to the n minus 1, plus dot, 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 and then plus a to the 1z plus a 0, and then is equal to 0. So that's like your characteristic equation, which remember we found the characteristic equation. It's the denominator of your closed loop transfer function. So that's what we have here. But what they do is the first step, step number 1, it's going to be make sure that a of n is greater than 0. If not, multiply by -1. You just need to make sure that your first coefficient, I literally feel like he's going to give us with the first coefficient -5 or something, just multiply it all by -1. So that's step number 1. Step number 2 is form the table. And so the table has 2 to the n minus 3 rows. So if you have a third order system, it'd be 2 times 3 minus 3. Okay, so n is just the order of your system. Then the next one's going to be, for your jury's table, it's going to be z to the power 0, z to the power 1, z to the power 2, dot, 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 z to the n minus k, and then z to the n minus 1, and then z to the n, okay? So what we're going to have here is we're going to start, it's basically a big table, and you're going to notice that starts from A0, A1, A2, and then A to the n minus k, A to the n minus 1, and then A to the n. Then in the second row, what you're going to see here, so that's just based off your characteristic polynomial. So notice that you start with the last coefficient, and then you get to the first coefficient, A of n. Then in the next row, you literally just flip it. So you just go an, and then you go an minus 1. So you're just flipping. And then you get a2. Okay. So now that we have that, then you do the next thing. So you calculate from the first 2 rows, then you can find, remember how for the Roth-Hertz, you can find in the next row, which here, if we have our B0, your B1, your B2, blah, blah, blah. And then it's going to be to your B n minus K. And then it's going to be to your B of n minus 1, then to, yeah, then it stops there. Because remember, you drop 1 every time. And so then it's going to be B n minus 1, B n minus 2, and then you got to go B n minus 3. And then you have B n minus 1, and then B0. Okay, so what we did is we just flip-flop, then you keep going down, 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 all the way until you get to an M0, an M1, and an M2. So you get to a second order. So that's how many equations you have. So what you need to remember is your B of K is going to equal A0, AN, and then A of N minus K, and then your AK. So if I have to solve for, let's say B1, let's just say B1 is equal to, it would be A0, and then we're looking at A, N, then it'd be A of N minus 1, and then A1, okay? So it's going to be these two, and then A of N minus 1, A1. So that would give me my B0 by finding determinant. So make sure you have those formulas written down that he provides in the notes for finding your determinants and having the jury's table. And then the third step, so after you form the table, you have to make sure that D of 1, it satisfies these conditions. So you plug in 1 for your characteristic equation here. It has to be greater than 0. And then -1 to the n of D of -1 is greater than 0. Okay. And so those are, and then you have to make sure that the other conditions are met, that A0 is less than A of N. Make sure you just write down all these conditions so you don't accidentally mess any up on your cheat sheet. B of N minus 1. And then your C0 is greater than C of N minus 2, and then dot, 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 all the way to M0 is greater than M2. Okay, so this is a little more math, of course, we have to apply, but it's good to know. So let's look at our system where we're given like the characteristic, because you guys can find the closed loop system. I'm not worried about that. It's more how do we apply the test. So we'll go by the rules with an example to sort of understand how this works. So say that for an example, we're given the characteristic polynomial d of z is equal to z to the power 3 minus 1.8 z squared plus 1.05 z minus 0.20. Okay, and so is the system stable? So what we first look at is a of n greater than 0? And so remember, for this particular one, this would be a to the n, z to the power 3 minus, and then this here is going to be for r's in particular, this is A3, A2, A1. Okay, yeah. So this is A3, this is A2, z to the power 2 plus, and then, or sorry, if this is plus, and then A1, z, and then plus A0. And so what we're going to see here is that our a to the n, which is a to the power 3, so our a of n is greater than 0. That's the first step, because it's a positive number. It's a positive 1 in front here. Sorry, this is an a to the 3. And so number 2 is form the table. So how many rows do we have? We have 2 to the n minus 3 rows. So plugging in, we have 2, it's power 3 minus 3 rows. So this is not a 6 minus 3. So we have a total of 3 rows in our jury's table. And so looking at the jury's table in particular, what we're going to have is we're going to start with the Z0, Z1, Z2, and Z3. And so because we're going to have 3 rows in our table, just already making what our table should look like, what we're going to notice from the table in particular is if we have 3 rows, we're going to be left with these last 3 ones here. And so this would be our A0, our A1, our A2, our A3, and then the A3, A2, A1, A0, and then we're going to have solve for that 3rd row right there. And so just copying down what we have, if we have A0, that's going to be our negative 0.20. And then our A1 is 1.05, our A2 is negative 1.8, and our A3 is 1. Then swapping the positions, you literally just flip-flop them, negative 0.20. Now we need to solve for the space right here, which is M0. So I'm going to call this spot M0, M1, and M2, just to follow the table. So M0 is defined as a table as it's going to be determinant a negative 0.20, and then it's going to be 1, and then over here it's going to be 1, and then negative 0.20. So what we're going to get, if you do this by the calculator math, you're going to get 0.2 times 0.2, and then minus 1. We're going to get negative 0.96. So negative 0.96. For M1, it's going to equal, what we're going to have here is we're going to have still negative 0.20 and 1, but now we're going to move it over to get our, because it's n minus k. So our k now is 1, so it'd be 3 minus 1, so A2. Okay, because I'm looking here, M1 would be equal to 0, this would be 2, and this would be 1. Okay, yeah, so L2 is going to be, looking within what we have here, it's going to be negative 1.8. And then L1 is going to be 1.05. So solving for this one, your M1. So what we did here is we just took these two and these two to get our M1. What we're going to have is taking the determinant of this, negative 0.2 times 1.05 minus, and then it's going to be negative 1.8 times 1, we get 1.59. Then your M through 2 is going to be equal to. Now looking at this, we have negative 0.20, 1, those always stay the same, the first column. But then now here in our third column, we're going to see specifically that this is going to be L1 and L2. So it's going to be from these two. So it's going to be 1.05 and negative 1.8. Taking the determinant of that, negative 0.2 times negative 1.8 minus. And then we got 1.05 is going to equal negative 0.69. Okay. And so that's what we get within our table. So looking at that, what we have here is now we need to solve the third condition, which we set up the table. So the third condition says that your D of 1 must be greater than 0. So looking at D of 1, D of 1 is going to be 1 minus 1.8 plus 1.05 minus 0.2 is greater than 0. So here we get 1 minus 1.8 plus 1.05 minus 0.2. I get 0.05 is greater than 0, which is true, so that's correct. And then the second condition you have to satisfy is that your negative 1 to the power of n, and then this is d of negative 1 is greater than 0. So we're to the power of 3 because we're a third order. So this is going to be negative 1 in front because negative 1 power 3 is negative 1. D to the negative 1 is going to be negative 1 to the power 3 is negative 1. Negative 1.8. Then if we plug in negative 1 here, negative 1 squared is just 1, so it's just going to be negative 1.8. Negative 1 minus 1.8. And then here we get plus 1.05 times negative 1, so negative 1.05 minus 0.20 is greater than 0. Okay, so now doing all this, we have negative 1 minus 1.8 minus 1.05 minus 0.2 times negative 1, and we get 4.05 is greater than 0. So check, we met those two requirements. Now, what we have to do is we have to look at the coefficients. So is a of n less than a n? And so what we're going to see here is that is a naught less than a n. And so our a naught here is that less than a n. So is a naught less than a n. And so what we're going to see is that our a naught is the absolute value needed 0.20 is less than 1. And so that is true, so we're good. Now we need to look at the next one, which says that B naught, which for us, it's going to be, because now we just have A naught and then we just have M naught. So we just need to look at, is our M naught greater than M2? What we're going to see here is our M naught is negative 0.96. Is that greater than our M2, which is negative 0.69? And we're going to see that, yes, that is true. So now that we saw that it handles all this, the system is stable. So we're good. So system is stable. So that's literally what the test tells us. It tells us that the system is stable if it meets all that criteria. So you have to form, basically from your characteristic equation, you make sure that the first coefficient is positive. If not, you multiply by -1. So we're good here. Then you have to form the jury's table, which is 2 to the power of n minus 3 rows. And so make sure that these two conditions are met. Form your table, which we did. And then the third one, you have to make sure these two conditions are met. Then based on how many coefficients you have, how many rows you have, you're going to have to keep reapplying this test to make sure that you meet all those criteria to determine that your system is stable. So now that we determined that, then our next one is basically looking at the root locus of our system. So the root locus is very standard in the two domains. Just make sure you have all the equations. And so we're going to start out basically with just solving a system, and we're going to try and determine our root locus from it. Just if he wants us to plot a root locus plot, we know how to do it. So for this system particularly, we're going to be given the following, where we have our R of S. And then we're going to have the inputs here. Then it leads to our E of S, which goes through a switch here. And we get E star of S. And we got 1 minus e to negative ts all over s. And then it's going to go through for GP of s. And then we're going to see that from here, we're going to get our output C of s. So what we have to do within the system is it says GP of s is defined as k all over s times s plus 1. And t is equal to 1 second for a sampling time. So it says plot the root locus. So what we have to do from here is basically when you have to do root locus plotting, we're a little familiar with it, is that first let's find the closed loop transfer function in order to get our basically our characteristic equation at the denominator. So what we're going to do here is we're going to solve, and so remember, this is just your G of S right here. So your G of S is going to equal, or G of Z, now it's 1 minus Z to -1, because we have a zero order hold, and then you have to take the Z transform, and it's going to be your GP of S all over S, okay? Which we can do. In order to do that, what you're going to get when you do the Z transform is going to be K T minus 1 plus E to negative T, Z plus 1 minus E to negative T, minus T, E to negative T all over. Then you're going to get Z minus 1, and then you're going to get times Z minus E to negative T, okay? So now we need to find the closed loop transfer function. So the closed loop transfer function in terms of Z is going to equal G of Z all over 1 plus G of Z. So what we have to do here is when you do solve this, what you're particularly going to get is you're going to get a pretty big equation. So leave it in the form 1 plus though. Don't simplify it. So leave it in the form 1 plus because that's going to come in handy. So it's going to be T minus 1 plus E to negative T and then times Z. And then plus 1 minus E to negative T minus T E to negative T. All over. And then here we're going to get Z minus 1. And then Z minus E to negative T. And then here we're going to have 1 plus K Then we're gonna have t minus 1 plus e to negative t, z plus 1 minus e to negative t minus t e negative t. All over, and then we're gonna have z minus 1, z minus e to negative t. And then what we're gonna have after here is we're basically going to look at, okay, this is important because when we have to do our plots of root locus, you get it in terms of the form 1 plus k and then L of s is equal to 0. So we found the closed loop transfer function, and I said don't simplify, like put this in over here because this is the format we want. And so what we're going to do is we're going to look at that specific one. So plugging in what we have here is we have our 1 plus k, and then here we have 0.3679z. If you plug in what our t value is, this is how I'm just getting these values, plus 0.2642 all over, and then we have z minus 1 times z minus 0.3679, okay? So now that we got it in this one, remember, this is our open loop system, our L of S right here. And so what we're going to see is when we plot the root locus specifically, what we're going to notice is that for our system, we're going to have a 0 when we start at gain k is equal to 0. When we just plot the open loop system here, when you plot the open loop gain, so plot L of z, you should have a 0 at negative 0.7181, and you should have poles at positive 1, because z minus 1 is equals 0, and then also positive 0.3679. Okay, so that's what we should expect when we plot the root locus here. For the open loop system, what you should see here is when you make your plot of the open loop system, you're going to be able to determine that, hey, from my open loop system, we have a 0 at negative 0.7181. And then you have a pole at positive 1, and then positive 0.3679. Okay, so now that we got that here, what we're going to notice is within our system, if we have to do the root locus plot, is we're going to get, now, we just have the open loop system, right? When k is equal to 0 right here, we need to find the asymptotes and also the angle of the asymptotes in order to have an idea of where it's going. And so looking at this, what we're going to do is remember how your sigma, your asymptote is going to be equal to, and then the number of poles, which we have 2, minus the number of zeros, which is 1. And then so here, your poles, you add your poles together, so it's going to be 1 plus 0.3679. Then you subtract your zeros, which are at negative 0.7181. Okay, and so right here, when you do this, you're going to get your value specifically at 2. And what about your angle of your asymptote? So this is just where your asymptote is located. So it's at 2. So we know there's an asymptote at 2 here. Sort of like an asymptote there. And so what about the angle here? So we are going to look at our angle specifically, and it's 2r plus 1 times pi all over your number of poles minus number of zeros. And so just plugging in r is equal to 0, you'll get pi over 1, so you'll get 180 degrees. When you plug in r is equal to 2, you're going to get 3 pi over 1, which is just going to be 3 pi is 180. And so it's the same thing. So it keeps repeating. So we only have the angle, the asymptote goes 180. So what we're going to see here is that it's saying that here's our asymptote, and the angle we're going to go from the asymptote is going to be here. So it's going to be along the 180 line. So what we should notice is that these are going to break what we're going to see specifically is that we're going to have these two go and break out, and then one of them's gonna go upwards and then break back in and go to this 0, while the other one's gonna go downwards, break back in, and go to infinity, because one of our asymptotes goes 180 degrees. So one of them's gonna go to infinity, go out 180, and the other one's gonna go to the 0. And so you can use the jury's test to find the range, or you can use the Roth-Hertz test to find, because remember that we have a unit circle. So if this root locus goes outside the unit circle, you find the k value when it goes outside the unit circle. But if you want to find these break-in and breakaway points, what you do is you take the derivative with respect to 1 over LZ and set that equal to 0. And that's how you would find it. I usually use MATLAB for that, though, in order to find it. So that would be how you could find that specifically. And then that's pretty much how you would do your root locus plot in terms of how you would actually have to get the red circles within the unit circle. For this problem, because we had to know which value of k, I remember I had that condition before, in which the system is stable. What we're going to see, find range of k for which the system is stable. Give me a second real quick. You have to apply the stability test to determine. So here, in order to determine if it's within the unit circle or not, because say if we have our general unit circle, and say for a unit circle, I know this is a bad representation of it, but notice how the root locus goes outside the unit circle at these 2 points right here, and well, should have been symmetric. But if the root locus in pink goes outside the unit circle, which is in like light blue here, those points, those k values are determined by the range of the, your Roth-Hertz or your Jury's test. Those will tell you the range of the k which your system is stable within. So the upper range of k for which the system then becomes unstable and goes outside the unit circle is going to be where it breaks out the root locus. So you'd have to apply the Jury's test to see the range of k for which the system then becomes unstable. Does that make sense, Fernando?
Yeah, it makes sense. Yeah, I was like wondering, like, damn. So basically, like, if the range falls outside, then it's gonna go out of the unit circle. But if the range is within, it's within the unit circle.
Yes. And so
right.
that's what, so basically, just walking through the last example here, I think it shows it a little bit better. So let's see. So he basically had his open loop equation here. He had a different one. And so notice that there's 1, 0 at 0.9048. There's 2 poles at z is equal to 1. So the summation of your poles, you're going to notice that we have 2 poles at 1. So 1 plus 1 minus your zeros. We only have 1 0, right? And then number of poles minus number of zeros. So this determines your asymptote. So we're expecting an asymptote at 1.0952. And the angle, your poles minus your zeros, you're going to only have 2 minus 1 here. And plugging in r is equal to 0, you're going to get pi over 1, which is 180. Then you're going to get 3 by repeating. He took the derivative with respect to 1 over LZ. You plug this into MATLAB and you find the value of the breakaway point, which you get. And so what you're going to notice, though, is he applied the stability test here. So from his characteristic polynomial, he applied d of 1, then he plugged in -1. And then since it's a second order, he just noticed that, okay, we only have to look then at right here, if this last term here, which is our a naught, is less than an, which solving for k, he got the value here. K has to be less than, looking here, it must be greater than 0 and it must be less than 0.2 to satisfy all criteria. And so then here within his system, you'll notice that we have our 1, 0 here. And then remember how we had 1, 0 in one pole. And so the pole, sorry, we had, here was 2 poles, 1, 0, my bad. And so remember that one pole was at 1, and the other pole was, sorry, 2 poles were at 1 and 1, 0 was about here. So he started plotting his root locus. So notice at the point 2, it breaks out of the unit circle. So that's the range of K for which then it breaks out the circle. So you have to apply your test. And so your test here, the jury stability test, you can get the ranges for your D1 when you plug in -1, and then when you plug in for your coefficients, and depending upon your value K here, that's how you're gonna find out what your range is, and that will tell you when you break out the unit circle. Does that make sense?
Yeah, it makes perfect sense.
Okay. Sounds good. And that's pretty much everything, honestly, for the exam. So, you just pause the recording.